Espera aí, vamos faltar aqui uma cadeira. Good morning, everybody. It's my great pleasure to welcome you to SenSys 2021, and I would like to give a word of thanks to, of course, our guests here, but also to the people that came in person to the conference, and of course, last but not least, to all the people around the world that are attending SenSys 2021. I would like to give the floor to the mayor of Coimbra, Dr. José Manuel Silva. Please.
Good morning, everyone. I'd like to welcome you to Coimbra, this fantastic city where more than 20 centuries behold us, with the third oldest university of the world, still working, still evolving, still working for the future, and to our city that it's world heritage, and where we are creating, also working with university, and welcoming you all to work for the future, for the smart cities. We created the Coimbra City Lab. We are working with private sector in order to transform this very old city in a future city where everybody can live and be happy. So welcome. I wish you all a nice conference, a very fruitful meeting, and hope that you feel happy in this city, and that you feel that it was worthy to come here, and that in the near future you can come physically to visit Coimbra. Welcome you all, and I wish you a very nice conference. Thank you.
Now I give the floor to my colleague Edmundo Monteiro that will give some words from the University of Coimbra.
Hello, good morning, everyone. I'm a head of department of informatics engineering. This conference is organized by two departments, the electrical and computer engineering and the informatics engineering. So it is a pleasure to see two departments cooperating to support this conference, to organize this conference. So I'm representing here the rector also. So the welcoming you in the name of the rector of the University of Coimbra to this conference. So the University of Coimbra is quite big. We have 9 faculties, and we are inside the Faculty of Science and Technology, that is more or less half of the university. And inside this Faculty of Science and Technology, we have 11 departments, many degrees, PhD students, BSc and master students. So it is quite big. We are outside the old university is more it's law and literature faculties, and we are outside in the new campus. And we I think we are a quite dynamic environment with lots of research labs and activities, and also conference organization. So I wish you all the best for this event, and also to enjoy the city and the university. And I think there is a visit organized also to the university to see the old university. So welcome and thank you.
Thank you very much. And now, please, the TPC chairs. Thank you, Andrew and Ron.
And thank you very much for the introduction. I'm Andrew Markham from the University of Oxford.
I'm Ron Sen from my Master University, Canada.
Great, and we've been given the singular honor of being the program chairs this year for SenSys 2021. And I'll just like to take you through how we went about constructing this program. So I'm sure, as you all know, ACM SenSys is one of the flagship conferences in this area. It's a single track conference, which means that it's highly selective. It covers all aspects of sensing, networks, and systems. This year has been made significantly more interesting, shall we say, through its hybrid format. So to have a mixture of in-person and online presentations. And the fundamental aim of the conference and the program is to try and retain the interactivity of a traditional conference with the ubiquity and the global reach of online attendance. So to get to actually choosing the papers that are presented in the program today, it is certainly a fairly long process. Our primary criteria to all the papers is to be robust and fair. And we have asked all the reviewers to be constructive in their criticism, so to fairly critique the work so that we can select the papers of the highest merit. Reviewers have been drawn from all over the world this year. We have a core TPC of 55 members, which is slightly larger than traditional census because, as you see later, we use a virtual TPC instead of an in-person TPC. So in terms of the interesting statistics, a total of 152 papers were submitted, of which 139 went through to full review. From this, we can start to see where our community is leaning. So in terms of the top 4 topics, we're looking at mobile and pervasive systems, learning algorithms and models, and new platforms and hardware design. In terms of the concentration of research topics, we're looking at predominance of data and devices, and by author domicile, we're looking at the US is by far dominating the submissions to this conference, followed by China and Singapore, and then the rest of the world. In terms of the review process this year, we did an accelerated 2-phase process. So we compressed the review cycle into 3 months instead of the usual 4 to 6 months. And this ended up having 627 high quality reviews written in about 2 months by the TPC, which is quite significant. So we certainly are deeply grateful to all those reviewers who gave freely of their time and their service and expertise. So this led to an average number of reviews per paper of 4.5. We then filtered out the top 67 papers to further discuss. And there was an online discussion phase through comments and in the conference management tool, followed finally by a virtual TPC meeting to refine these decisions. So finally, we ended up with 25 papers selected. And then these go through a further 1-month shepherding process from TPC members to improve the quality of the camera-ready papers. And as you will see, we have all aspects of systems covered from practice to theory. And it is an exciting and ambitious program of papers that we truly hope you will enjoy and be inspired by. This year, we've had a new innovation, and I'll hand over to Gianpietro to introduce that.
Thank you. I'm Gianpietro Picco from the University of Trento, and together with Pei Zhang, whom you see there on the slide, I'm the co-chair of the journal track. The journal track is something new that, as Andrew mentioned, we are starting at SenSys this year. Is a I cannot. Thank you. Is a new track in the main program that is not handled regularly, meaning through the process that Andrew and Ron just highlighted, but actually targets papers that have already been published in selected journals with 2 expected benefits. An expected benefit for the journal authors, of course, which typically have not presented their paper in a journal, in a conference. And so they have a way to effectively disseminate their archival publication and interact in person or hybrid this year with authors, with attendees, and then for the attendees themselves, which have a complement to the normal regular track of the conference. So the journals that we partnered with this year are two, and this ACM transaction on the Internet of Things and ACM transaction on sensor networks. And this is something that is expected to go on in the next edition of SenSys, as discussed with the steering committee. So let me give you a little bit the process that we followed and the outcome that we had this year. So in terms of the papers that are eligible to this track, you may have seen the advertisement. Basically, we set a limit that any paper published in those two journals that they mentioned 2 years earlier was eligible for presentation to the conference, or also journal paper that are accepted for publication. The application process was very, very simple because, of course, the paper is already published. And so it consisted basically of filling a form and declaring, basic information about the journal itself. Then, as far as the selection process is concerned, we basically was performed by the track chairs, so by Pei and myself. It is what was not a review because, again, the paper had already been reviewed and published, and so it was just a way to try to select the papers that best fit the program. And as I will tell a little bit more later about the constraints that we had in this respect. In terms of the accepted presentations, those are their papers are not published in the proceedings because, once more, they have already been published, but they are linked from the program and from the web. But apart from that, they are treated just like regular papers in the SenSys track. So they have to have a SenSys teaser videos, and they will have the same amount of presentation as the regular track. Now, this was the process that we had to set up this year for the first time. And so the outcome was surprising to ourselves. We had 49 submissions, which is a lot, okay. There were basically nearly split evenly between the two journals that we partnered with. As I mentioned, this is many more than we expected. And so we had to do, okay, move on. We had to do some compromises with all of this. So we had to consider only papers that were not extensions of other papers. So privileging basically people that have never had the chance to present their work in front of an audience. And still there were 21 of them. And then we had to organize them in parallel tracks, which is what you see effectively today. Overall, we accepted 8 presentations, which is still 16%, which is unfortunately low. We'll see if and how we can do it next year. Again, these are unintentionally split between the two journals, but please, because this is the first time that we do something like this, provide us feedback after the journal track to us in presence or at the business meeting that will be later on in the program. Thank you.
So in addition to the technical session and journal track, we also have 2 keynote and 1 panel we have top expert in this field. And we also have a post and demo, which is going to be split into 2. One is in person and 1 is virtual. So in addition, we're excited to host N2 Women meeting, which is scheduled on Tuesday afternoon. So next, we're going to get to one of the most exciting moments of the conference. That's a Best Paper Award. We are lucky to have €500 prize for the winner. The Best Paper Award, given the high quality submission and the accepted paper, is really hard to decide which are the top candidates. So we have a rigorous selection process. The best paper is selected double-blindly by a committee of 5 TPC members who independently rank each candidate paper. And the final ranks are used to decide the winner and the runner-up. So out of the 25 papers that are accepted in the program, we have narrowed down to 5 best paper candidates. In the interest of time, I'm not gonna name all the authors, just announce the title of the paper. So we have new LoRa towards ultra-low SNR LoRa communication with neural-enhanced demodulation. 1.5, one-shot recognition for unseen gesture via COS Wi-Fi. Limo BERT unleash the potential of unlabeled data for MU sensing application. RF fusion, robotic grasping via RF visual sensing and learning. Last but not least, we have via voice, a noise-resistant multimodal speech recognition system fusing millimeter wave and audio signals. So out of those 5 papers, we have selected the runner-up award goes to Lim and Yu. Is it shown? Goes to Lim and Yu, unleash the potential of unlabeled data for MU sensing application. The paper is going to be presented in session 5. The authors are Huatao Xu, Pengfei Zhou, Ritian Molly from Nanyang Technology University, Guobing Shen from Alibaba Local Service Lab, Alibaba Group. So let's give a round of applause of the runner-up. Okay, now is a moment for the Best Paper Award. It goes to Neural LoRa towards ultra-low SNR LoRa communication with neural-enhanced demodulation. The paper gonna be presented in session 2. The authors are Chenying Li, Huang Qinggao from Michigan State University, Shuai Tang from Tsinghua University, Xiao Zhen, Zhichao Gao, Mingjiang, Qiben Yang, Lin Xiao from Michigan State University, Jinliang Wang, Yunhao Liu from Tsinghua University. Another round of applause, please. So as mentioned, that the paper was finally decided by a panel of 5 TPC members. Here, I'm just going to highlight some of the comments from our award committee. So they consider the paper is impressive and a novel approach that has practical community contribution and has a potential for major impact to a fundamental mechanism for sensor networks and mobile computing. Another member comment that the paper consists of good use of computational solution to low-level communication problem in LoRa. And one comment that this constitute a real-time, real-world applicability and impact and nicely realized and effective. So last but not least, we would like to give special thanks to the organizers and steering committee who shepherd us every step of the way. We would like to thank TPC reviewers and external reviewers for their timely efforts. The review load is pretty heavy. We would like to thank all the speakers and panelists, obviously all the authors, as well as the audience and participants online and in person. So now I'm gonna turn to Jorge for the introduction of the keynote.
Okay, once again, welcome to Coimbra. I hope you enjoy the conference. It's the first time that we are organizing an hybrid conference, and believe me, it's very, very hard and very risky. So I also would like to thanks to the organization, to the committees, to the City Hall, and a very, very special thanks to the volunteers, okay? Our PhD students that are doing a very great job. So I'm going to present Luca. Luca Mutola is an associate professor at Politecnico di Milano, Italy. and a senior researcher at RISE Sweden. His lab focus on modern networking embedded system, including intermittent computing, nanosatellites, mobile embedded computing, internet-connected robotics, and low-power wireless. To date, Luca is the only European researcher to be granted multiple times with the ACM SenSysBuildSys Research Highlight and to ever win Best Paper Awards at multiple flagship conferences of both ACM SenSysMobile and ACM SenSysBet. Is the general chair of CPS IoT Week 2022 and the past PC chair of ACM MobiSys, SenSys, IPSN, EW European Wireless Sensor Networks. Is also associate editor of IEEE transactions on mobile computing, ACM transactions on sensor networks, and Elsevier computer networks. Okay, thank you very much, Luca.
It says I cannot start the screen sharing because someone else is screen sharing. Not yet. Still says there's someone else screen sharing.
You're not screen sharing? You're not screen sharing?
I don't know. It says that there's someone else.
Wait.
Can I start? No. Oh, maybe now it works. Yep. Okay, can you give me a green sign? Everything is working also for the remote users. Okay, thanks. So welcome everyone, and thanks a lot for the introduction. It's very exciting for me to be here today, not just because I was asked to open the conference with a keynote, but also because I feel privileged to be able to do this in person. You know, after like almost 2 years of pandemics and virtual conferences, it's nice to be here and then looking at so many familiar faces. So what I want to do today is to have a conversation with you on the role of science and engineering in embedded sensing. And it might seem, you know, a little bit of a bold objective, but I think it's the right time to do that. And let me tell you why. So the next edition of ACM SenSys is going to be 20th edition, and the community is healthy and thriving. But exactly because of that, I think it's time we grow up. It's time that the body of knowledge we're building is made a little bit more established and systematic. And I feel that is crucial for us to achieve a long-term impact. But when I start thinking about that, central to this reasoning and to these reflections on my own is the role of science and engineering in embedded sensing. It's hard to precisely define what science and engineering exactly are. So you can argue that science is some sort of systematic enterprise that organizes organizes knowledge in forms of explanations of the universe, the physical world. For example, natural scientists formulate hypotheses on how the world behaves based on observations, and then they confirm or refuse those hypotheses based on further observations, and that's the role of a scientist. Engineers, on the other hand, or at least engineering science, is more about trying to discover something that doesn't exist by making an attempt to build it. And here I'm not talking about the practice of engineering, which is more about reapplying known methodologies and processes to solve problems that we know can be solved. This is more about the endeavor of discovering something new by trying and building it. Someone told me once that if you know it works, it's not research. And that's just another way to put it. So the apparent contrast between science and engineering was eminently kind of described by Theodor von Karman in a quote, in a sentence. Theodor von Karman said that scientists study the world as it is, whereas engineers create the world that never has been. And my objective today is to try and distill the essence of what Karman used to state and apply it to embedded sensing. Hopefully, giving you some food for thoughts and some inspiration to perhaps change the way we do research in our specific field. And the reason why I think it's important to do that is because I feel that the dichotomy or the apparent dichotomy between science and engineering is a gross approximation. Okay, I've seen like system papers being dismissed because it's just engineering, or theory papers being ignored because whatever they describe is not practical. So in many ways, I think we are, in many ways, I think we're getting this whole thing wrong, and that's affecting our potential to make a long-term impact with embedded sensing research. I feel there are three fundamental aspects that come into play here. And I have three main messages for the community. One is, how do we intertwine science and engineering in the experimental methods we use in our research? Second is, what is the kind of scientific contribution we can find in engineering systems? And third is, how can we plan our research so that the engineering discipline is useful for the science and vice versa? In the rest of the talk, I'll try and dig deeper into these three aspects, and I use examples taken from my own work, not because I think it's the best, but because it's the one I'm most familiar with, and I found myself often struggling in between the many conflicting forces between science and engineering in the course of the projects I'll be talking about. My fundamental claim here is that science and engineering are not to be contrasted with each other. They are not just complementary, they are actually a necessity, one for the other and vice versa. So let me start digging a little bit into how science and engineering meet when we use experimental methods for our research. So it may be argued that experimental methods are what distinguishes hackering and tinkering from true science. In general, experimental methods include hypotheses, some sort of instrument that is used to collect data, and a systematic analysis that, based on that data, confirms or refuses a certain hypothesis. Don't get me wrong, but for example, I feel slightly disturbed when I see papers claiming the evaluation to be a contribution. I think in many cases, perhaps not all of them, but in many cases, the evaluation is a necessity. So it doesn't really make a lot of sense to claim it as a contribution unless it's designed, for example, to push a system to its limits and find where that system breaks down. But that's not really often the case. And in certain subfields of computer science, we've been very successful in using experimental methods. There's a marvelous piece written by Peter J. Denning about the science in computer science. And he analyzes a couple of cases where experimental methods have been used in very systematic ways to the point that the hypotheses have been made, have been established. And one example is queuing theory. In queuing theory, we have accumulated the experience that confirms unquestionably the models based on observations of how concrete systems work. We are very far from that point in embedded sensing, and let me give you an example taken from my own research. Some years ago, we started working with drones, and we have been looking at drones essentially as a way to move sensors in space. So we were using drones as a form of mobile computing platform. One crucial piece of software that's running on a drone is the autopilot. The autopilot is a little piece of embedded software that runs on an embedded board on board the drone. And what it does is really simple. It reads the values of the navigation sensors, for example, the GPS sensor or the IMU, based on what's normally a PID controller, decides how to operate the motors on the drone so that, for example, a certain pattern is traveled in space. But when we started looking at that piece of technology, we were quite unhappy with how it worked. It was very unreliable, very inaccurate. So we started looking more closely at how autopilots actually work. And we realized something. Even though the autopilot nominally runs a PID controller, it's the proportional component of the PID controller that bears the greatest effect. The other two components, the integrative and the derivative components, provided that the sensors are sufficiently calibrated and you have a proper balance of the weights on the drone, they actually play a much more limited effect on the control logic. So we came up with a hypothesis there. If that's the case, if our observation is indeed true, can we make the controller reactive? What does that mean? If what matters is only the proportional component, can we kind of discard or almost completely ignore the other two and make control only a function of the instantaneous sensor readings? That was our hypothesis, which eventually led to a concept that we called reactive control, where the idea was basically to look at the changes in the instantaneous sensor readings and decide based on that whether the control loop had to be run again, or we could just stick with whatever control settings were output by the control loop at the previous iteration. That, in principle, could give us a lot of advantages because we could, for example, spare unnecessary executions of the control loop, or conversely, like increase the control frequency wherever like big changes in the inputs were recognized because, for example, the environment was throwing something at us and the drone had to react more quickly than usual. In order to verify these hypotheses, there were a number of major challenges that we had to overcome. For example, what does that mean that we have a significant change in the sensor inputs that demands another execution, a new execution of the control loop? Or how do we regulate this reactive execution over time so that we do reap the advantages without affecting the dependability of the drone? And ultimately, how do we implement all these efficiently so that it can run on a resource-constrained embedded device? Let me give you an example of how we tackled the first challenge. Because in there, we made another hypothesis. At the beginning, we tried to look at the details of the control logic, and we quickly got lost. Because even though this software is running on a resource-constrained computing device, it's actually a pretty complex piece of software. It's hard to track all the dependencies. It's hard to track the data pipelines. The executions are highly asynchronous. There's like events being triggered at random points in time. So any effort at explicitly modeling the behavior of an autopilot turned out to be a failure. So we were something wrong with Zoom. Okay. So we were basically facing a modeling problem. Autopilots are actually quite sophisticated pieces of embedded software. And this work was like between 2014, 2016. If we were doing this now, we would probably try and throw some machine learning at this thing and hope to build a model out of whatever data we have. But machine learning was not fashionable at that point in time yet. So we tried and made another hypothesis there. Can we look at the autopilot as a black box and pretend that whatever happens inside the autopilot is a random process? We knew it was not random, okay, because the executions were deterministic. But we kind of felt that inherently the processing was so complex that it didn't make any sense to try and model it explicitly, but it was probably more meaningful to try and look at it from the outside. So these random phenomena that we conjecture was the right way to model the behavior of an autopilot had an input and an output. The input was where the changes in a single sensor readings, and the output was whether a binary value telling us whether the control decisions had to be changed or not, which in turn dictated whether we had to rerun the control loop or not. And we ended up being able to model the behavior of an autopilot according to a known statistical distribution that's called logistic regression. It's really simple. The plot here shows the relation between the extent of changes in the inputs versus the probability that you do need to rerun the control loop because you need new settings for the motors. And the shape here actually mimics or reflects the intuition that we can possibly have. So if the changes are small up to a certain point, then the probability that you do need to rerun the control loop is also small. But there's a point where, after some specific threshold, the probability kind of grows rapidly, and for very large changes in the input sensors, it's almost certain that you do need to rerun the control loop because you need to change the way the motors are operating. So reactive control boils down to looking at these shape and decide where, based on the extent of the sensor, of the changes in the sensor inputs, whether you do need to rerun the control loop or not. So if you just draw a line in between and say, okay, for whatever changes we recognize in the sensor inputs that are above this threshold, we do run the control loop. Otherwise, we don't do it. That's the essence of reactive control, which again was entirely based on a hypothesis that we could look at the autopilot functioning as a random phenomenon. And luckily, the specific shape of this curve is described by a pretty simple analytical expression where there's only two parameters that need to be estimated. And we found ways to obtain pretty accurate estimations for those two parameters, and you find the details in the paper. So we had our hypothesis. Now we had to build the instrument to collect the data. So we implemented reactive control on a number of different drone platforms and a number of different autopilot software because we wanted to prove that the concept was general, that it was applicable no matter what was the kind of drone or what was the kind of autopilot platform we were considering. And eventually got to a point to collect data that luckily confirmed the initial hypothesis. In this chart, you see an excerpt from an experiment that was like 10 minutes long. The blue line here describes the frequency of execution of a traditional autopilot that is fixed, for example, 400 Hertz. With reactive control in a setting where we could observe increasing wind gusts, reactive control was accordingly increasing the average rate of execution. And that was exactly what we were hoping for. Reactive control was progressively recognizing increasing larger and larger changes in the sensor inputs and accordingly increase the average execution rate. Conversely, in a much nicer setting in a lab, the average frequency of running the control loop with reactive control was lower, but you see also spikes here where reactive control pushed the frequency of the execution of the control loop even above the traditional setting. And those were the times where the drone was actually flying next to the air ducts in our lab and being affected by the forces of the air flowing from there. It was quickly reacting by increasing the frequency of control loop executions. So why did I want to tell you all this? Because luckily we were ultimately successful with reactive control, but we essentially walked in the dark because we had absolutely no established baseline to compare with. We had no well-defined metric to be able to collect the data useful for confirming the hypothesis. And mobile drones were and still are kind of an emerging mobile computing platform, so it's totally reasonable that we don't have anything established in this specific field. But I think it's time for our community to work on the methods more than on the systems themselves. I think we need, at least for the major subfields in our area, we need to define reference scenarios. We need to define benchmarks that people working in the same area can relate to. And those scenarios and benchmarks and metrics that are defined accordingly need to be technology agnostic. It makes no sense to come up with benchmarks and metrics that are too tied to a specific technology, because by the day that technology is no longer in use, then the methods also become essentially useless. And we also need to build infrastructure that would allow us to run those benchmarks in ways that the results are comparable with each other. We have been in contact with many people trying to extend reactive control, trying to build on it. And most of the time, I can tell you, was not invested in technical discussions. It was invested in how to create the right setup that they could use to obtain data that was comparable to ours. The thing is, unfortunately, there's very little incentive to do this, and this is something we need to fix. One way, perhaps, is to make it a community effort. I cannot pretend that a single research group kind of invest the resources necessary for the benefit of the whole community. But perhaps if we join forces and we devote a little bit of our time to the benefit of the entire community, that's perhaps something that can work. And I wanted to mention an initiative that is really going in that direction. IoT Bench is an initiative that was born some years ago with the goal of establishing benchmarks and the underlying infrastructure for repeatable experiments and comparable results in low power wireless. Sure, that is limited to that specific field, but it's already very valuable that those guys and those people have been investing efforts in this direction. And if you're working in that area, I would really encourage you to get in touch with them and perhaps contribute to this initiative. They run yearly workshop located at CPS IoT Week. You can, for example, join the discussion there, or just contact them directly. So the next aspect I want to investigate is whether we can find, or how we can find, a scientific contribution in engineering systems. And here I want to be a little bit controversial. I would argue that the scientific contribution of engineering systems is not in the system itself, it is in the discoveries and in the lessons that are learned in the process of building the system. And I want to push this to the point of claiming that the system in itself is largely irrelevant. It's not really so important that the system works very efficiently. It's not so important that the system is something that is practical or useful. And even worse is the case where we judge systems based on whether some imaginary end user would eventually start using it. That's not the point. Of course, if a system is useful and works efficiently, fine, that's a nice plus. But the crux of the problem here is really in the discoveries and in the learning process that happens when we build systems. And, to learn from system building, I think we really need to push things up to real deployments. And I might sound a little bit, I might sound like I'm contradicting myself here, because I just told you that the system in itself is irrelevant, that it's the process of building the system that matters. And now I'm telling you that you need to build something that can be deployed for real in realistic conditions. And everybody knows that that's really a pain and it requires a huge amount of effort. The argument here, however, is that if we build systems that are not thought to be deployed, then the learning process that I was mentioning before is essentially unfinished. Okay, we really need to go the whole 9 yards and push system engineering to the point that we build things that can be deployed. Then if the deployment in itself doesn't happen, it's a different thing, but the system in itself must be thought to be deployable at least. And, we tried and exercised this principle in our work in intermittent computing, because especially in intermittent computing, and this is like I complain also to myself in a way, learning experiences from building systems that are thought to be deployable or can be deployed or are being deployed are very rare. So let me tell you a little bit of what we did in this area. And I want to start with a little bit of history here. What you see in the movie here is the Circus Maximum in Rome. That's the place where people in Rome, back in the Roman ages, used to attend chariot races. And the place was like digitally reconstructed in many blockbuster movies. What you see there is Ben-Hur from 2016. And the place still exists today. only the ruins remain, of course. And what you see over there, the building, is a workshop for the Opera Theater in Rome, where they build the backdrops and the sceneries for the theater. And what's interesting for us is a place underneath there that's called Mithraeum of the Circus Maximum. The Mithraeum is an archaeological site. It's considered one of the hidden gems of Rome. It's part of the UNESCO heritage site in Rome. It was discovered by chance, and it's totally underground. It's composed of a number of like small communicating rooms covered by barrel vaults. And what you see here is the ground floor of the workshop of the Opera Theater that sits on top of the Mithraeum, and these concrete columns are actually standing right on top of the barrel vaults. Our deployment experience there starts with the municipality approaching us because they wanted to reopen the site, but before doing that, they wanted to have data on the structural and environmental integrity of the site. So what really mattered for them were the integrity of the barrel vaults that was potentially affected by the vibrations of the concrete columns that were supporting the ground floor of the Opera Theater, and the temperature and humidity patterns. That was because the restoration processes needed to have that information as an input to decide how exactly to go about preserving the integrity of the site. And in addition to that, we had severe constraint in terms of placement because it's actually hard to kind of jump on top of those barrel vaults and install sensors, or we couldn't really place temperature sensors anywhere we wanted because we didn't want to affect the visual fruition of the art pieces in there. And as I'll tell you in a second, this place has very peculiar temperature and humidity patterns. It's underground and it's closed most of the time. So what you have there are humidity levels that normally go above 90%. Working in there is a pain. I don't know if you have ever stayed in a place where 90% plus humidity for more than a couple of hours. It becomes hard to breathe. And when we were working down there, we had to go out and have a walk every couple of hours because it was becoming difficult to breathe in there. So we have deployed a number of 18 sensors in total. 6 of them were recording vibrations and inclinations on the concrete columns, whereas the remaining ones were monitoring temperature and humidity at different places in the site. And we took these as an opportunity to exercise our research in intermittent computing. We started with a battery-powered system that we call the Kingdom, that we deployed in January 2017 and is still operational today. At some point, we have deployed an energy harvesting system alongside Kingdom that we called Republic, but that turned out to be a total failure. It just didn't work. Based on what we learned from the deployment of Republic, we eventually deployed another energy harvesting system that we called Empire that is still running today. Let me tell you about what we learned in this process. From the battery power system, we learned 2 important things. First was that whenever there's energy, now embedded sensing works. It just works. We have learned how to do things. The papers like the Hitchhiker Guide to the sensor network deployments have taught us how to do things. Now it works. But kind of ironically, what doesn't work are the batteries, because in a place like that where there's 90% humidity the chemical batteries just behave crazily. You cannot really rely on the fact that they have a certain amount of charge at some point, because like 5 minutes later they'll stop supplying any energy. So we turned to energy harvesting, deploying thermoelectric energy generators. Thanks to the fact this was kind of peculiar, about 40 centimeters down the Mithraeum, there's a layer of concrete that's called Roman concrete that is the archaeologists conjecture is the same that can be found at the circle maximum outside at about 10 centimeters down the ground, from the ground level. So effectively, the circus maximum acts as a huge thermal surface that connects the outside to the midstream underground. And that was something we have exploited to generate energy from thermal gradients. And we also deployed vibration energy harvesters, commercial ones. We bought them. We didn't do anything special for them, powering the sensors with the accelerometer and inclination sensors. This was in the first iteration. We pretended just to swap out batteries for energy harvesting. We didn't do anything more than that. We didn't touch with, or better, we touched the software only, when it was really necessary. But everything else, including energy management and the actual sensing processing and the way we were managing energy in situations of energy scarcity, remained the same. And because of that, we learned things the hard way. Executions become intermittent because you cannot continuously rely on a supply of energy. So you have to deal with patterns of execution where there's a phase of charging the capacitors on board that up to a certain threshold where it's possible to start running, but then the net balance of energy while you're running decreases because there's not enough energy supply to sustain the computation for long. So at some point you die and the whole thing restarts all over again. We had to take care of that. We have implemented the so-called checkpointing mechanisms, but things still didn't work. They didn't work because we realized that this is not something you can really find in the literature, that whenever you do, you have to do with intermittent executions, it's not the processing that matters, it's the way you handle peripherals. Because the peripherals are what is really going to consume the greatest amount of energy, and reinitializing the peripherals, even if you're not going to use them in that power cycle, becomes a huge energy waste. Moreover, as I mentioned before, we did not touch the software where it was not necessary. And one of the early design choices was, okay, when the current sensing iteration is over, we are going to sleep. And that remained in this iteration of the system. But that was not a smart choice, because sleeping in a situation of energy scarcity makes you consume energy for nothing. And what we have observed is that the sensors were going to die while sleeping very often. And the energy consumed while sleeping doing nothing was essentially gone for nothing. And third, which is perhaps the key lesson we learned at this point, was that energy harvesting is not necessarily decoupled with the events that you're interested in. And that was particularly the case for us for vibrations. On the vibration, on the sensors equipped with accelerometers and inclinometers, vibrations were both the quantity to sense and the source of energy. And that was something that we had sort of overlooked in that iteration of the system. So we went back to the whiteboard and completely, redid things with a total new design, including custom hardware that, for example, included ways for the software to control the energy levels at which the node was going to activate. And the software was then also in control of how, when and how to shut down the sensor. The sensor was previously shutting down only when there was no more energy to keep computing, but we wanted to gain control on that, and we built the hardware to enable that functionality. We also had on the nodes with accelerometers and inclinometers, an additional custom board that we built to attach another piezo that was not there to generate energy, but just to activate the sensor. With the trigger piezo, we had ways for the sensor to wake up when a certain vibration was being recognized, no matter what was the energy level at that point. If it was sufficient to do something, fine. Otherwise, okay, that was a nice try, but at that point, there's nothing more you can do. And as a result of this hardware redesign, we also redesigned the software. We turned from a checkpointing-based approach into a task-based pipeline, where the single tasks were running with transactional semantics and were connected by non-volatile data pipelines. And that was necessary because by splitting the functionality into loosely coupled tasks, we could schedule their execution based on the actual energy available, based on how much energy was this circuit communicating to the microcontroller at the time of activation. The scheduler was deciding whether to run the sensing process, the data processing functionality, or the actual transmission, no matter what was the original ordering of execution of these three functionalities. And with this third iteration, we learned something more. We learned that whenever you are in a situation where there's really little energy, you need to be in control of that energy. You cannot just turn on and execute when there's enough. What is enough? You, as a software developer, need to be able to determine what is enough and for what. And to do that, you need to have the hardware that does that for you. So it doesn't make a lot of sense to isolate research intermediate computing on the hardware or on the software, because what we realize is that you need to co-design the two, or there's no way out of, at least in the scenarios that we have been considering. And because of the task-based architecture, we were also able to selectively activate the right peripherals only when they were actually needed. If we knew that we were going to run the sensing process, then we were going to turn on the sensors. Otherwise, those sensors were not going to be reinitialized, and we were not paying them the energy necessary for doing that. And perhaps the last but most important lesson we learned was that whenever there is some coupling between the source of energy and the quantity to sense, you do need to capture that coupling. That's what we did with the trigger piezo. And it turned out to be the key for the efficient operation of the system. The efficient operation of the system that's pictured in this plot, where you see the amount of data produced by the system normalized to the amount of data produced by the battery power system. That was our baseline in that case. What you see there is that both of the energy harvesting design iterations produce very little data compared to the battery power system. Republic, for example, was producing about 15 to 20% of the data produced in the same time period by the battery power system, but it was not the amount of data that mattered. It was the quality of the data. Because Republic had no way, for example, to capture the coupling between the energy source and the quantity to sense, the acceleration data obtained by Republic was useless. The structural engineers said that they were getting data at times where there were no vibrations, and instead where there were vibrations, the system was off. This was not the case in Empire, because thanks to the trigger piezo, we could actually activate the sensor when there was a vibration of interest to capture. And there was another interesting phenomena that you see down there. In March 2020 and onwards, you see a drastic decrease of the amount of data produced by the sensors equipped with accelerometers and inclinometers. And that's because that was the first wave of COVID-19 in Italy. The country, as you probably know, entered a very strict lockdown. All the activities were suspended, including the ones at the workshop of the Opera Theater. The vehicular traffic was basically non-existing, so the vibrations basically faded away. They disappeared. So there were no ways for the sensors using the vibration harvester to gain the energy necessary to compute. But because of the trigger piezo, we could actually wake up at the right time. And the right time was a day when a earthquake of moderate intensity occurred in an area north of Rome. And the vibrations of that earthquake propagate all the way to the Mitraeum, and the trigger piezo kind of turned on the sensor at that point, even if there were no not a lot of vibrations to our response. The sensor remained silent, accumulating energy all the time where there were no vibrations of interest, but the earthquake was indeed of interest, and that was the time where the piezo triggered on the node. And the vibration data we have gained, we use the data to compute the Richter magnitude of the earthquake as seen by our sensors in the midterm, and it turned out that our estimate was 314, pretty close to the official ones that reported an interval between 3.2 from 3.2 to 3.7. Of course, the official estimates are obtained with professional seismographers scattered all over the places. This estimate was obtained by our energy harvesting system that we did not touch since it was deployed first. It was totally autonomous. Okay, what is then the message to the community? Now you'll be thinking, okay, very nice, but where do I find a nice application? Where do I find a deployment target? The key here is to look outside the box. Embedded sensing is useful in so many ways that you can really help a lot of people. You can help archaeologists, you can help structural engineers, you can help medical doctors, you can help almost any discipline. The problem is you need to get out, you need to communicate your work in ways that is understandable to people outside of our community so that they can appreciate what we do and perhaps find ways to collaborate. Of course, it must be clear from both sides that there's some research going on. What happened to me quite often when I talk to people outside of my community is that they pretend me to kind of do the grant work and deploy a system that they pretend to be working totally fine since day one. No, that's not the point. It must be clear that they are doing research as well as you are doing research. So what you are gonna provide to them as an embedded sensing system is not something that is like commercial grade or is next to the efficiency and reliability of a product. But if you can establish a common ground on that basis, then at least in my experience, it's immensely valuable to work with people outside of our community. And it's a massive effort. It goes without saying that it's a pain. It requires a lot of resources. At Polytech in Italy, in the Italian system, PhD students must graduate in 3 years. The deployment I just described has been running for almost 6 years by now. So it's not reasonable that one PhD student is allocated 100% of the time on a deployment effort. And it's a risky undertaking. But because of that, I think as a community, we need to reward these experiences a lot more. We cannot pretend to hold experience and deployment papers to the same standards as the more regular technical papers. And what I wish to see are the negative lessons too. We have a mindset that only things that work are valuable. That's not the case. Our discipline is one of the disciplines where it's most rare to find papers about negative results. In medical sciences, there's plenty of papers about negative results, and those are very valuable also. It's like we are pretending that only the things we do right are important, but that's not the case. And as a perhaps corollary for that is that, for a message not to the community, but to hiring committees, is that we should probably stop punching papers with many authors if they are experienced in deployment or deployment papers, because again, they're not the same kind of paper. It's not the same kind of effort. We need to have a different basis to judge those papers. So let me then going towards the conclusion here by telling you a little bit how we can find ways to have engineering at the service of science and vice versa. This is based on a personal experience. So in science and in computer science, the literature goes like long way glorifying principles and abstractions, even to the point of calling them a form of art. There's also a notion of aesthetic computing, and Donna Knuth has vastly talked about the relationship between science and other disciplines, including religion. But there's a difference from this kind of science and the more general concept of science. The science we do is hard to make systematic forever. The way we verify the principles and the rules we develop is by applying them to concrete systems, which is eminently an engineering effort. And most often we cannot pretend to kind of conceive principles that are general. We need, however, to test them against the passing of time. I wish that we could develop principles that are not just applicable to the system we build today, but to the systems that we will build in the future. Something like this happened to me recently. So in 2009, I published a paper at IPSN about programming framework for disconnected operation in sensor networks. A sensor network that works in a disconnected fashion is essentially a system that has very rare chances to connect to the backend and report the sense data. And I had developed a programming system and a programming framework and a runtime system to build that kind of applications. But then something happened. All technologies like LoRa, Sigfox, all the very long-range wireless technologies that we have today started appearing. So the scenario, the idea of having a sensor network so far from any point that you could connect to the rest of the internet kind of disappeared. So what's left then of that work? I was lucky because roughly 10 years later, I started working on a different kind of disconnected system, nanosatellites. Nanosatellites are a new breed of embedded sensing system that is in contrast to the, is in contrast to the large satellites that we used to build until the early 90s. With small satellites, we have a different kind of platform that is more effective and efficient along many different dimensions. With a small satellite, it's easier to isolate failures. They're easier to schedule in terms of launches, and they're robust to budget fluctuations. The way it works is just that one builds a small satellite and there are collective efforts to launch them in space. If you are ready in time for one launch, fine. Otherwise, everybody else is going to be launched and you wait for the next turn. In a large satellite, you would have to keep the entire project on hold, even if a very little piece of the big thing was not ready. But that's not the case with the small satellites. There's one key problem with small satellites: positioning. Now, you might think, okay, you have GPS, but a CubeSat, which is a very specific kind of small satellite, travels at around 7 to 15 kilometers per second. And the GPS satellites also travel at around 3.8 kilometers per second. So the relative movement of the two creates a situation where the Doppler range, the Doppler search range is like 4 to 5 times the one you have on Earth. To make things worse, the small satellites do not have any, or often do not have altitude control. So they keep tumbling. They tumble all the time because they have no way to control. They just orbit, and they are subject to passively subject to the forces that happen to be in space along the trajectory they are flying. So the visibility of the GPS satellites also changes very rapidly because the GPS antenna is normally only on one side of the CubeSat, and this thing keeps tumbling all the time. And the GPS, of course, takes energy. So people use duty cycling to abate the energy consumption of the GPS receiver. And that further complicates matters because without a continuous position tracking, then often you lose the ephemeris, almanac, and all the GPS information. So every time you turn on, you basically start from scratch. And all these factors contribute to make the time to the first fix much longer, which in turn is detrimental to energy consumption because you need to keep the GPS receiver for long.
What we have done was to build a system that we called Hummingbird. Hummingbird is a hardware software system where, in a nutshell, what happens is that while the GPS receiver is off and the CubeSat is working in a totally disconnected fashion, via software, we simulate the trajectory of the CubeSat. And when we turn on the GPS again, we have at least a rough idea of what are the GPS satellites that would be visible when we turn on the GPS. That allows us to reduce the time to the first fix because the search range is reduced, and therefore to save energy. We have been lucky enough to go the whole 9 yards again, up to a real deployment on a CubeSat that we call the Nano One with not much ingenuity. That was launched in 2019. And what you see there is the energy consumption of the GPS receiver in 3 different configurations across roughly 5 hours of operation. The bar on the left is the energy consumption of the GPS receiver if you keep it always on. The one in the middle is like naive duty cycling when you turn on the GPS receiver every 50 minutes, but you don't do anything more than that. Our system consumes this amount of energy instead, because the time to the first fix when we turn on the receiver is much reduced, because the software simulated navigation of the sensor allows us to have a better idea of what would be the GPS satellites in the view of the CubeSat when we turn the receiver on. So what is the message to the community in this case? I wish we could write and talk more about what's next rather than what we have done in a paper. I've seen, so what I tend to see very often are papers that make a big deal of like tackling an important problem, finding a solution, and evaluating the solution. That's all fine, that's great, but let's not be too short-sighted. We should exercise the principles, the concepts in perhaps multiple settings. Of course, they do not be complete. It's not like we need to build systems for what we have today and what we'll have in 5 years. But I think a little bit of additional effort in the direction of thinking, what we build today, how what we build today could be used in 5 years is something that's worthwhile to do. And wrapping up, I want to show you again the statement by Theodore von Karman. And I hope I conveyed how important it is to reflect a bit more on the mutual relationship between science and engineering, especially on the basis of the 3 aspects that I've been talking about today. The 3 messages I have to the community perhaps are our starting point. I sincerely hope that they will trigger more discussion now in the rest of the conference and perhaps in the future. But I do think that we should seriously address this if we really want our community to grow up, as I mentioned at the beginning. And before I conclude, I wanted to show the faces of the many people who worked with me over the years. Of course, what I told you is not just my own contribution, but it's definitely a team effort that over the years involved a number of different people. Yeah, this concludes my talk, and I'll be happy to answer any questions.
So we have time for some questions.
Hi, good morning. In the first part of your talk, you mentioned IoT Bench as a successful way to benchmark different systems in the wireless domain, which are systems that can be tested more or less in isolation from the rest of the sensor node. Do you think this is possible also in the energy harvesting domain, where there are many more interdependencies, the size of the transducer, the materials, the converters that you use, and also the environmental things, aspects that it just explodes in terms of the size of the design space.
So, of course, it's not like everything can happen immediately, and we need to start from somewhere. In the domain of energy harvesting, for example, we don't have energy traces that everybody agrees on. Okay, that's ridiculous. So it's if we want to run a simulation of whatever system that uses energy harvesting and find how it reacts to different energy patterns, we don't have publicly available, or we have very little publicly available energy traces. And that's a domain where we do need a lot of that, because the variety and diversity of the energy sources is so great that we would ideally need, traces from like vibration harvesters, and traces from solar panels, and traces from, RF energy harvesting. And that's not something we have. So, for example, let's start from that. I do think that would be a valuable starting point, but we need to get going.
Thank you.
Hi, Danny Hughes from KU Leuven. I'd like to kind of zoom in on a particular phenomena that you talked about in the presentation, to talk about the science engineering bit a little bit. So I think it's a fascinating talk, and we speak a lot also in the lab about the same thing. But one thing that worries me a lot is the difficulty of pulling apart results that occur for very specific reasons around a site or the way that something was built versus things that are really true and generic.
Sorry, can you keep the microphone a bit closer?
Sure.
I cannot really.
Sorry. So the difficulty of pulling apart results that are truly generic versus results that arise due to the many complexities of a site deployment. So for example, if you take the battery reliability issue in Circus Mithrium, it's fascinating. And I love battery-free systems. We like to build them. But is there a scientific hypothesis behind the reason why, for example, in a high humidity subterranean environment, a battery fundamentally is less reliable than a supercapacitor?
So I can tell you what we did. When we observed that behavior with chemical batteries in the Mithraeum, we went to the chemical engineers and asked, can you explain this? And they were like, sure, it's known. Okay, why? And then they started drawing equations, telling us, oh, but this and that, and that. Fine. The question, the point is, that's probably something that they knew. We have discovered it the hard way, but where do we meet? We need to have like the chemical engineers in this case teaching us in ways that are understandable to us what we can expect from chemical batteries in that kind of environment. That was extremely hard for us. They know that that's the case and they can explain it, but to a level of sophistication that is not useful for us. On the other hand, okay, we have discovered it the hard way, and that was kind of a good excuse for us to experiment with energy harvesting. But had we known that beforehand, we would have probably skipped the design and deployment of the battery power system altogether. But by doing that, many of the lessons we have learned will not be there.
Absolutely. So I agree completely on the latter part. But the only thing I'd say on the former part is there's a lot more people even than the chemical engineers, of course, because you have people who deal exclusively in PCB reliability, the finishing of cases, designing cases that can breathe and exhale moisture, and so on and so forth. So, and then I'll stop talking so much, but that brings me to industry as well, because I think the only place where you can realistically kind of pull that level of data, where you can compare side by side high humidity environments and different power sources, has got to be from people who are paid to deploy them, because otherwise it becomes for us kind of an insane task. So I wonder if you have any thoughts on how that can be kind of pulled into our ecosystem more.
I hope I understood the question, because it's really hard for me to
understand
from here. So the speaker is actually facing your way. But so let's see if I understood the question or the comment. Perhaps something that I haven't touched is the relation with the industry. And there are things that industry knows but doesn't tell anyone. Probably because they have no incentive to do that. And I don't want to be overly pessimistic, but if industry doesn't talk to us, perhaps it's also our fault. It's our fault because you know, we are there crammed in our offices running simulations, and we don't really, you know, make visible to them that what we do is useful for them as well. So there's no mutual exchange of knowledge and systems that they find useful talking to us. That is something that honestly I've been struggling with myself, and I fortunately have no solution rather than you know, keep trying. We need to find a way to convince them that what we do is potentially useful for them, so they're happy working with them.
Thank you.
Hi, Luca. Thank you very much for the talk as well. Because of course, as you know, people publishing in Sensys like me, I also get a lot of comments saying, well, this is a lot of engineering and most of it never makes it into the paper as well. So it's quite vindicative to hear that. My question is around, I guess, the rise of using machine learning in much of our work, because there's a lot, of course, in engineering and in designing a real world system, but we also move a lot towards black box modeling and things that we cannot introspect. So I'm wondering whether you have any thoughts in how we can make, you know, all these models that we use in these deployment situations more applicable to the community as a whole, because we build a model, we use it, and it's, you know, further applicability in a new scenario is not yet clear, and we don't have to, you know, we're not required to release our models or our data. So I'm wondering whether you have any thoughts on the future of how we're moving and using ML for all of these applications. Thank you.
So one thing, for example, that I wish we could do more is to make the data from the deployments available. The energy traces we have from the Mitreum are being made available, and I'm, you know, it's partly my fault if they're not online already, because again, it's an effort to kind of clean the data, make it, you know, just provide some even skimmy documentation or anything. One thing that we could do, for example, is that one. Data meaning both, for example, the energy traces I mentioned before, but also the system logs. We have quite a good amount of system logs for certain like periods of the deployments where basically everything that happens inside the system is visible. I wish that we could make that available, and then perhaps someone else could take that up and perhaps apply some machine learning to that to see. One thing we are curious of, for example, is the relation between certain system events and the energy patterns, because that's not something we can really explain from the semantics of the code. So there must be something else that happens there and we cannot explain it. That's something that would be valuable. I think it boils down to sharing more, sharing data, sharing system designs, sharing you know, system logs and all that kind of stuff.
Okay, thank you.
It's Prabhat at UC Berkeley. Thanks, Luca, for a wonderful, wonderful keynote that touched on a little bit of philosophy, a little bit of current debate, and looking into the future. I did want to dig into one thing about batteries. You and I have struggled, I think, in our lives with batteries a fair bit.
Sorry, over there because it's I understand what you're saying.
Sure. So thanks for a wonderful keynote. I wanted to ask a little bit about batteries. So, you know, you talked about negative results, and I have a MobiCom negative result paper actually basically on batteries and phones plugged in for a long time that all got bloated. And my laptop now is bloated from being plugged in for the last year and a half. So the question is, you know, you gave all the set of lessons from your experience, and one of them was, well, if the batteries work, it's great. But batteries are the problem, and there's like 7 or 8 or 9 or 10 things after that, earlier about energy harvesting and programming and living around that. But if we now go back full circle and say, okay, a lot of the electronics have gotten more efficient. You've got a bunch of nice programming techniques. If we could actually use the right batteries for the job, might not all of the great things you've done actually make battery powered systems so much better? And in fact, shouldn't we be engaging with the chemists and asking them what are the right, technologies to use for our applications, as opposed to, let's say, using lipos in the wrong way and plugging them in all the time? And I think that this is really key, because if you go back, right, a lot of the work in this field really started with the energy constraints, and the energy limitation as being the fundamental problem which justified so much of our other work. And I think it's now a good time maybe for us to go back and say all the great work we've done, how does the underlying technologies in those areas change? So just wanted to get your thoughts on that.
Actually, I can only agree with you in the sense that when we talked to chemical engineers before we started using energy harvesting, our question to them was, is there a battery we can use there? And they said, okay, yeah, there's this prototype that exists in one piece. We can lend it to you for 1 week. That was not the point. So I definitely agree. And again, it goes back to one of my messages. We need to look outside our own field and talk to other people, because otherwise, I don't want to be overly pessimistic, but there's so many fields that kind of died all alone. And it's fine if, when a new field emerges and all the new things pop up, that the field keeps moving always in the same direction. But it's almost 20 years we're doing this. It's time that we grow up and we talk to other people, including the chemicists and the chemical engineers. This is something that I'm trying to do myself. It's extremely hard. I don't know if my perception is general, but at least in my experience, chemical engineers are one of the hardest people to talk to. But again, I think we really need to make an effort in that direction.
So the question actually is a little broader than that. Certainly we should go and talk with chemical engineers, but also all of the great development that's happened, assuming intermittency, assuming extremely limited availability. You have these great ideas around passive vigilance and triggered operation. Those would all be great, wouldn't they, if we use batteries, and maybe not in such an extreme environment, but we might be able to use much smaller batteries in slightly less hostile environments too. And I think that's what the bigger part of what I was getting at is not just the technology base, but applying all the things. It's like when the Mach OS system, in order to get Mach to work really well, the folks at CMU made all these tricks to improve its performance and then compared it against the OS and then said, hey, look how great Mach is. But they never actually went and applied all the great things they did to the existing OSs and found out how much better those would be. So I'm really sort of encouraging both, not just the energy harvesting train, but applying those, to the state of the field more broadly. But that's the essence of the point.
I hope I got your last question, but indeed, I also feel there is a tendency we have of, attacking a problem, finding a solution, that's it. But we never go back there and see if the new things that pop up in the meantime could make the solution we originally conceived to that problem simpler or more efficient. So in our case, for example, it's not an absolute need to use energy harvesting. If we had a way to use more traditional batteries and more regular programming frameworks, that would be great. It would make lots of things simpler. But as you said, I take, it's my fault. We didn't go back there and looked at those things, but you should definitely do that.
Thanks for a great talk.
Rong Sen from McMaster University. Thanks for the great talk and the reflections. So my question is regarding the experimental design that you advocate earlier. I'm kind of being a little playing the devil's advocate a little bit. So my question are twofold. One is that given this many years of engineering experiences and industrial practices, do we really need to reinvent the wheel here, or it's just a matter of probably synthesize successful practices or method and then apply to our community? And the other side of the question is that given the application domains that researchers are working on so diverse, so is there any hope to have a cohesive set of experimental method that this community can adopt?
So about the third question, you're right in saying that we have accumulated a body of knowledge now that it's probably possible to synthesize the research work we have done up to this point into like a set of, for example, metrics and guidelines and benchmarks. But the problem is the effort to do that is often underestimated. And nobody dares to do that because it's not a little effort. This synthesizing of the body of knowledge we have in a more systematic and established way is not trivial at all. I've been in contact with the people of IoT Bench, for example, at the early stages, and I wish I could, have collaborated more with them. But I've seen how much they were struggling in at least establishing an initial framework, an initial set of metrics, an initial set of benchmarks. What I'm saying is, I do agree with you, but the problem, the crux of the problem is that nobody dares to put the effort in there. And as a community, we should do that because, again, we want to keep prospering and not like die out like many other fields have done in the past. And then coming to the second question, it's definitely, I do agree that the landscape and the spectrum of potential applications is huge. But again, based on the experience of IoT Bench, what I can tell you is, okay, start from something. You're not going to be as general as you wish. You're not going to be as comprehensive as you wish, but something is better than nothing. There will be application scenarios that in your experimental frameworks are not accounted for. As long as you acknowledge that and you state it up front, that's fine.
Thank you.
I don't know if we have questions from Slack, from remote people. Okay, so we thanks again to Luca. Okay, guys, it's now time to a coffee break. Okay, the coffee break will be served on the first floor. Okay, thank you.
the Já estou a fazer isso, é?
Não é isto. Papadinho. So, welcome to technical session 1 of SenSys 2021. We're going to start this session because we are under a very tight schedule. We have 4 papers and we have 90 minutes. So we have to start immediately, and I would take this opportunity also to ask the presenters. All the presenters in this session are remote, but ask the presenters to not try not to exceed 20 minutes, and then we have 2 minutes for questions. I know it's very difficult and it's very tight, but please try to comply. So this session is on, the title of the session is Distributed Computing and Learning for Sensing Data Processing. The first paper, you can see the title here, and the presenter will be Neiwen Ling. Neiwen Ling is a 4th year PhD student from AIoT Lab in the Chinese University of Hong Kong. Her supervisor is Professor Guoliang Xin. She is also the N2 Women Fellow for SenSys 2021. And her research interests include real-time artificial intelligence, edge artificial intelligence, and edge computing. Neiwen Ling, please go ahead. Welcome. You can start your presentation.
Okay, thanks, Chair. Can you see my screen?
Please go ahead. We are seeing your slides.
Is it okay now? Okay. Hello, everyone. Today, I'm going to talk about RTMDL. This is a joint work with Kai, Yuze, Daqi, and my advisor, Professor Xing. Deep learning models are increasingly deployed on the edge device for many critical applications, such as autonomous driving, smart roadside infrastructure, and embedded computer vision. Despite the limited computer resources, edge devices may need to run multiple deep learning tasks concurrently. For example, to achieve autonomous driving, a car needs to run speech recognition and action recognition at the same time. However, those tasks have different types of DNA models and also need to meet highly diverse real-time accuracy requirements. For example, on-road collision detection is very critical and has very tight deadlines. So we must ensure deadlines are met as much as possible. At the same time, it also needs to achieve high accuracy. However, tasks like driver voice control may have a loose deadline and tolerate more deadline missing. Considering those challenges on the edge, the question we would like to answer in this work is how to efficiently support mixed deep learning tasks on the edge in real time. To support deep learning tasks on the edge, extensive works focusing on individual model compression, which checks the model accuracy for execution time. However, such approaches do not consider resource contention among mixed deep learning tasks. For example, if the edge device already runs some models, when a new deep learning task comes, if it cannot get the resource, whatever it is compressed or not, it still cannot be finished in time. A common way to address this real-time issue is assigning priorities to different tasks. However, real-time scheduling is not well supported by current deep learning frameworks like PyTorch, TensorFlow. Moreover, conventional real-time scheduling treats each task as a black box and cannot utilize the resource efficiently. The key novelty of our approach is to take advantage of the unique characteristics of mixed deep learning tasks. Here, we will show several important observations. First, the time for deep neural network inference can be adjusted by model compression. As shown in this figure, deep neural network usually consists of multiple layers, such as convolutional layer, fully connected layer. It can be compressed by reducing the width of each layer, thereby treating accuracy for lower latency. These figures shows the latency and the storage of VGG19 on the different levels of model scaling. As we can see, CI is a significant trade-off between latency and accuracy. We also test different models and find this kind of trade-offs are highly diverse across different DM models. Second, real-time performance of mixed deep learning task highly relies on the scheduling policy. We evaluate the real-time performance of mixed deep learning tasks based on the deadline missing rate. As shown in this figure, we run 4 different deep learning tasks at the same time. 2 tasks are based on AlexNet, and the others are based on VGG. We set different priorities to each task and plot bars of deadline missing rate on these settings. For example, this bar shows the deadline missing rate of AlexNet on all possible priority assignments, and it has high variation. It's also same for other 3 tasks. What's more, task-based scheduling alone cannot effectively support mixed deep learning tasks. As shown in this figure, an end-to-end deep learning task consists of pre-post-processing on CPU and model inference on GPU. Our study shows that CPU portion in task delay accounts for almost 30% for AlexNet-based deep learning task, and CI is up to 36% waste of GPU resources for executing deep learning models one by one. Motivated by our findings, we propose RTM-DL, a new real-time deep learning framework. Now I will overview the system of RTM-DL. Given a task set with different deep learning tasks, we first generate a series of model variants for each task on the storage bound. Each model variant has different latency, accuracy, performance. We then optimize the deep learning execution strategy. Execution strategy here includes task priorities and the scaling level for each task. We propose a new formulation that aims to find the optimal execution strategy that minimizes the accuracy loss while meeting deadline missing rate and the storage bound. More details of problem formulation can be found in our paper. RTM-DL also includes a new priority-based deep learning task scheduler to improve CPU-GPU resource utilization on edge platform. Now, I will introduce each component of our system. The first component of our system is storage-bounded multi-level model scaling. First, we scale the architecture of a basic model. Specifically, for each model, we can scale the model from width or depth dimension, and in this way, we create a series of model variants. However, such a series of model variants will occupy large storage space. The key challenge here is also model variants must to be stored at edge platform so that we can optimize them at runtime. To address this issue, we propose a fine-grained weight sharing approach, as shown in this figure. For shared model weights, we will only store the weights of the original model. And for private model weights, we will store all the model weights of each model variant. We then search for the number of model variants and the number of shared DNA layers to bound the total use storage. To meet real-time requirements and minimize the overall accuracy loss, we then search for the optimal execution strategy. Execution strategy includes two aspects. First, model scaling level, which is achieved by selecting model variant for each task. Second, task priority for each task. Assigned task priority will be used in our task scheduler. We then design a multi-objective evolutional algorithm to search for the optimal strategy. A key challenge here is that it's very difficult to analyze task deadline missing rate. There is no formula to give a deadline missing rate, and the current solution is very conservative. We address these challenges by adopting multi-objective optimization and performance approximation techniques. At runtime, we continuously collect profiling data from edge platform, and then we use this data to iteratively train the ProKIS model. The ProKIS model can predict deadline missing rate for each execution strategy. With the ProKIS model, we then use an evolutional algorithm to search for the optimal execution strategy. Motivated by our observations on the unique characteristic of deep learning tasks, we designed a new priority-based scheduler. This scheduler includes independent CPU, GPU task queues, and a new GPU packing approach. The advantage of our design can be shown in this example. When we treat each deep learning task as a single task, we may end up with task deadline missing, refers to deep learning task 2 in this figure. Our scheduler divides the deep learning task into the CPU subtask and the GPU subtask. In this way, the CPU subtask with low priority can be executed when the high priority task finishes its CPU subtask and starts its GPU subtask. Motivated by our findings in low utilization of GPU resource, we also designed a GPU packing approach to improve GPU spatial utilization. In this way, we can utilize the CPU-GPU resource more efficiently. In summary, RTMDL supports mixed deep learning tasks on the edge by joint scaling and scheduling. Given a task set with different deep learning tasks, first step is scaling basic model. At the same time, storage is bounded. Next, we try to optimize the strategy of execution. We use evolutionary algorithm with deadline missing rate predictor. Last component is the task scheduler. We use independent task queues and pack the GPU tasks in certain way. Thus, we increase the CPU-GPU resource utilization. We test the RTMDL under different settings. The first table shows the edge platform we used. The second table shows the deep learning task type, DL models, and the data sets we used in our experiments. We first studied the performance of joint model scaling and scheduling. We evaluate our system with two state-of-art baselines. On the light workload, our solution meets more deadlines than baselines. At the same time, it achieves more accurate. On the high workload, our method even gives much better performance. In summary, we can reduce deadline missing rate by more than 40% with very little accuracy loss. It shows that the idea of joint model scaling and scheduling is very effective. Take a look at the generality of RTMDL. We can see our system achieves the best performance among different DL model combinations and edge platforms. Detailed results of RTMDL evaluation can be found in our full paper. Our end-to-end system evaluation is an autonomous driving test bed. We can see from this figure, this is an F1 tank vehicle that installs two cameras and a single LiDAR. One camera will detect the traffic light on the right side of the car, and the other will detect the left side. To do that, we use several DN models. We also run two traffic sign recognition tasks on the preloaded dataset. Totally, there are 4 deep learning tasks running on this car. This is the demo video of our end-to-end system evaluation. On the left corner, we can see our system can detect all the traffic lights correctly. In contrast, the baselines will miss some traffic lights. This end-to-end system evaluation shows that our system has good performance for mixed deep learning tasks on the edge in real time. In conclusion, we propose RTMDL, the first framework that supposes the mixed real-time deep learning tasks. RTMDL includes joint optimization of model scaling and task scheduling, and a new priority-based real-time task scheduler. We also deploy RTMDL on an F1 tank test bed. We also discuss some future works, for example, extending RTMDL to uncertain workloads and dynamic scheduling. Thanks for listening. Please refer to our paper and the lab website for more details.
One minute or 2 minutes for questions. First, the audience. Are there any questions? Here. In Slack channel, No questions? Maybe I can do one. When did you showed a very interesting video, but in the lab, have you tried anything in well, in the real world? Are you planning to do this at least with the live vehicles, or what are your plans?
Yes, we conduct the experiment in the room. This is an experiment in the room. And our lab also has a smart lamppost in outdoors. We may deploy the RTMDO system in our smart lamppost to conduct some experiments, but it's a future plan. Yeah.
Okay, thank you. There's one question. Can someone bring the mic? Or I can. Okay, good.
Thanks for the talk. Can you comment on the overhead of running the optimization online? For the joint scheduler?
Yeah, this is a good question. So overhead for optimization can be we will so optimization for execution strategy can be conducted offline. And then we can find the optimal execution strategy on the current setting. And when the setting changes, we can again find the optimal strategy. And we can switch the execution strategies at the runtime to support different settings of task sets.
Do you want some more?
I guess the assumption is that the task set is not going to change, or at least you know ahead of time. So would there be a situation like you have something like an accident, that's something you did not anticipate, as such that the task set has to be updated and the optimization will have to be run online?
Yes, this is a good question. And actually, we have discussed this situation in our future work. So details also can be found in our paper. So main idea of handling uncertain workloads is that we can add a runtime monitor for uncertain workloads and adjust the model variants at the runtime.
No more questions. So let's thank Nayuan. Thank you very much.
Thanks.
And now we can move on to our next speaker, which I think is Lin 2, is it? Okay, Lin 2 is currently.
Yeah.
Okay. Currently a PhD candidate in the Department of Computer Science and Engineering at Michigan State University. His research lies at the intersection of cyber-physical systems, embedded artificial intelligence, and information processing, with a focus on interdisciplinary applications in health and in the environment. So please go ahead. Thank you.
Thank you. Okay. If you cannot see my screen, please interrupt me. Hello, everyone. I'm Lin Tu. This is a joint work with Xiaomi Ouyang, Professor Jiayu Zhou, Yuze He, and my advisor, Professor Guliang Xing. And today I'm going to introduce FIDL, Dynamic Layer-Wise Federated Learning for Human Activity Recognition. Human activity recognition has lots of applications such as healthcare monitoring and smart home systems. And these systems usually need to recognize a wide range of activities like medicine taking, indoor-outdoor activities, and meal events. These kind of activities normally using ambient sensors and body-worn sensors. So considering most of the sensing data in this scenario are multidimensional, deep learning methods are often needed for accurate human activity monitoring. However, current approach is mostly based on centralized learning that requires the user to send raw data, which impose significant privacy concern. So how about we store the data locally? Federated learning is a new machine learning paradigm. It enables collaborative model training while keeping the data residing on devices. In federated learning, user upload local models instead of data sets to the server, and the server learn cloud models by averaging combining all the local models. However, the single global model is not accurate for all users, as shown by several recent papers. Moreover, transmit the model weights back and forth will cause significant communication overhead. So to deal with these limitations of federated learning, we have two key insights. One insight is that there exhibits intrinsic similarity among users' activity data due to like human biological features, physical environments, or like sensor biases, as shown in the recent papers. And we test one human activity recognition data size and visualize the data distribution of 6 users' data. And from this figure, we can see that there exists a clear grouping relationship among the 6 users' data. And such similarity among users is also reported on other human activity recognition data sets, as shown in recent paper. So based on this kind of observation, we think like we can improve the learned model accuracy by facilitating collaborations among similar users. Another key insight is that the degree of the similarity among users' deep models reduced from the bottom up, as shown in the paper 4 and paper 5, which suggests that we can exploit such similarity of models and aggregate them in an iterative layer-wise manner rather than like aggregating whole models. As shown in this figure, 2 users only share their lower 2 layers as their model upper layers are more user-specific. We now exploit different model sharing schemes and their impact on model accuracy. We tested on data of like 6 users from the Hardbox datasets and visualized the relationship among 6 users' data through a correlation matrix by computing the Pearson correlation coefficients between each pair of users' data. And we can see that there are 2 groups, and the user within each groups are of different degrees of similarity. And this observation inspired a dynamic sharing structure where only the user with a similar data distribution should collaborate in learning, and users who are more closely related to each other will share more layers of their models. So based on this idea, we designed a new scheme like layer-wise sharing. And we implement more sharing structures and compare them with layer-wise sharing. We see that the model based on layer-wise sharing structure gives highest testing accuracy. So motivated by these results, we attempt to generate the layer-wise sharing structure from user relationships to improve the model accuracy. However, the correlation matrix of users' data in the left figure, this figure is like global information that cannot be obtained on a server without accessing the data of users. So we designed a dynamic sharing scheme to learn the similarity of users' model weights and generate the layer-wise model sharing structure accordingly during the federated learning to improve the model accuracy. We named this dynamic layer-wise federated learning system FedDL. FedDL learns the grouping relationship of the local models and then merge only the lower layers of the model in a bottom-up layer-wise manner. And now I'm going to introduce the hierarchical training procedure of the FATDL. First of all, the local model of each user is optionally initialized randomly or from a pre-trained model. Then FATDL going to perform model grouping and model merging in a bottom-up layer-wise manner. So first, it performs the grouping for the first layer, and then merge the first layers of the local models according to the grouping results to get a stable models. And then it computes the grouping results for the second layer and merge the models with the lower two layers sharing according to the grouping results for the lower two layers. And this kind of like iterative model grouping and model merging process gonna repeat till reaching the output layer. So for this case, it's only 3 layers. So like in this picture, I only show like 2 layers process. And each model aggregation involves 4 steps as shown in this figure. First, user perform multiple epochs of local training and then upload local models to the server. And then the server gonna group user based on the model affinity obtained from models testing results on a common sample size using KL divergence. And after that, the server compute the weighted average of local models based on the grouping results, and then generate further personalized model through the weighted average of the local models and their corresponding average models. And finally, the server transmits the personalized model back to the user for local training. And next So next we're gonna introduce the two components. One is like user grouping, and the other one is model merging. So FATDL learns the underlying relationship of users based on their model affinity. Normally, the element-wise weight distance like L1 or L2 norm have been widely adopted to measure the model affinity. However, they have like a severe limitation in modeling affinity of deep models because the neurons of each layer in hierarchical models are permutable. Besides, it's computational inefficient to measure the norm distance of high dimensional weights for complex hierarchical models. Therefore, instead of like directly analyzing the weight matrix, FATDL tests all local models on a reference distribution in the form of a common sample size, and then measure the model affinity using the KL divergence of the different model outputs. So based on the grouping results, FATDL merged the local models in a layer-wise manner. This figure illustrates the layer-wise model sharing at the server. So first, based on the grouping results of the lower 3 layers, the local models from the user in the same group were gonna be merged by computing the weight average. And the weight average coefficients of each group member indicates how close the member is tied to the group. And also after merging the layers of the models into shared models, the server gonna further personalize the shared models for each user by aligning each local model with its corresponding group model. FATDL take advantage of the dynamic layer-wise sharing scheme to improve the communication performance. Specifically, FATDL reduced the number of the parameters that each user needs to upload to the server. From this figure, we can see that only the lower 3 layers of the models are necessarily transferred between server and users during the model merging iterations, which will significantly reduce the overall communication overhead during the federated learning process. Besides, FATDL further reduced communication overhead by stopping the upload of each model's user-specific layers whenever possible. And moreover, the model trained using FATDL converge fast, even with a small number of local training runs, which is detailed in the evaluation. So FATDL can use a small number of global training runs to reduce the communication costs without like reduce the accuracy. For the experiments, we evaluate the performance using one self-collected data sets, LiDAR data sets, and 4 public real-world data sets for deep learning. We design and implement a FATDL phototype on Amazon Elastic Compute Cloud, and we build a server on the instance and run each user end on one CPU to simulate the federated learning. And the communication between the server and users is implemented locally using sockets. We adopt randomly initialized convolutional neural network for the human activity recognition tasks for all these 5 data sets. And the CNN neural network is composed of 2 convolutional layers, 2 full connect layers, and 1 softmax output layer. And we compare the performance of FATDL with 4 baselines, including federated averaging, federated learning with lower K layers sharing, and federated transfer learning, and also local training approach. First, we validate the design of FATDL on the LiDAR data sets. Specifically, we compare the performance of FATDL with the 4 baselines. And we observe the overall accuracy and also the communication overhead of different approaches on LiDAR data sets. First, we can see that FATDL achieved best accuracy performance with a mean value equal to 0.98, and the interquartile range is also very low. Besides, it's also showed that FATDL saved about 42.6% communication overhead compared with the FAT average and the p-FAT mean. In FAT average and p-FAT mean, they both share the entire models during the federated learning. And we further evaluate the performance of FATDL on different data sets, including the UWB data sets, depth images, and 2 IMU data sets. We can take a closer look at the hardbox data sets first. So as shown in this figure, the mean accuracy of FATDL outperforms other learning paragons. For example, it outperformed by like 25.8% to FAT average and by 12.5% to p-FAT mean. Besides, for this, the effective of the communication optimization, FATDL is also able to maintain a relatively low communication overhead. So both like FATDL and FATPER have a relative low communication cost for all the other data sets, because they only share part of the model layers among users. So similarly, FATDL outperforms other learning paradigms when applied to other data sets. And to verify the scalability, we evaluate the performance with increasing number of nodes. First of all, the accuracy performance, we can see that in our configurations, the mean accuracy of the FATDL outperforms other approaches. Besides, FATDL has a smaller variation of accuracy, which means that it can improve model accuracy for most nodes. And for the communication performance, when the number of involved nodes increases, the communication cost of other methods increases dramatically, while the FATDL maintain a relative low communication overhead, which verify the scalability of FATDL. The number, also the number of the local computation runs is a critical hyperparameter in federated learning. The setting of this hyperparameter shows a trade-off between the computation and the communication. To understand how these attributes affect the convergence of different federated learning methods, we conduct the experiments on depth image data sets with increasing number of local training runs. And this figure visualized the change of testing accuracy over global runs with different setting of local runs for a specific user. We can see that all the methods have improvements in convergence when involving more local runs. And also FATDL will always converge fast, even when the local computation runs is that small. In conclusion, we propose FATDL, a dynamic layer-wise federated learning system for human activity recognition. And it captures the similarity of users' models and generates personalized user models through dynamic layer-wise sharing in an iterative layer-wise manner. And this layer-wise sharing scheme can also improve the communication efficiency. And we also discuss some like future work. For example, first, to investigate the trade-off between privacy and the utility for correlated user in federated learning. Second, to extend the FATDL to a wider range of applications where the user's data have a high level of dynamics while exhibiting significant similarities. And for more information, please refer to our paper or visit our website. And thanks for attending our presentation. Any question?
Thank you very much, Lin. Are there any questions? There's one here.
Thank you for a nice talk. Can you please go to slide 11? I'm not sure whether I got that. Have you paired the models?
Right.
So 11. Yes, so you define a validation set and you, correct me if I'm wrong, but you're calculating the KL over the validation set between each two pairs of users, right?
Yeah.
And then you make such clusters.
Yeah.
Okay, and then how this averaging working? So just blindly averaging the models, like linearly interpolating? What is this averaging?
Here we not simply average the local models. We average, it's a weighted average. The key point is how we calculate the coefficients. The coefficients here is like when we when we grouping, like for example, for the first layer, it looks like all the users belong to one group. But the things like for each user, their coefficients is different. Their coefficients is reflects how close this each node's bonded to this group. And if it's bonded closer to this group, that means like this node's local model gonna contribute more to the average model, to the group model. But if this node's bonded less to the group, it's gonna contribute less to this group models.
Okay, and this averaging means averaging the weights, right? So you
N1
and N2. Okay, but correct me if I'm wrong, but if you blindly average them, like we know that N1 and N2 are residing in one basin, do you know that they can average? Because if you blindly average them, then there would be a barrier. So if one is 99%, the other one is 99, and you've averaged them, that you wouldn't get better than random chance. My question is that how this averaging is working. Like these are two separated models, right? On two different on one data set. So if you average them, it's not working.
So like different users model is on different data sets, first of all.
And this is not pre-trained, or is it pre-trained?
It's not pre-trained. It's like randomly initialized. It can be pre-trained. It doesn't matter. It's like a pre-trained or pre-trained or randomly initialized. Because first of all, before you merge them, before you upload to the server, your local models already been locally trained based on your local data. So they are different. They reflect each user's data distribution.
Okay, thanks. Maybe we can continue offline. Thank you.
Okay, thank you.
There's one question in the Slack channel.
In Slack, Junlu asks if this approach also applies to recurrent neural networks.
Yeah, It works for any deep, like hierarchical models, like deep models.
Okay, thank you. So if there are no more questions, let's thank Lin. Thank you.
Thank you
very much. And we can move on to the third paper of the session, which will be presented by Xiao Zheng, I believe. The paper is entitled Mercury Efficient On-Device Distributed DNN Training via Stochastic Importance Sampling. Can you put... Okay. Xiao Zheng is a PhD from Michigan State University. His major is electrical engineering. His research focuses on efficient on-device machine learning, federated learning, and AIoT. So, Xiao Zheng, please go ahead.
Thank you, Chair, for introduction. Can everyone hear me?
Yes, please go ahead.
Yeah. Okay. Hello, everyone. My name is Xiao Zheng. The title of my presentation is Mercury Efficient On-Device Distributed DNN Training via Stochastic Importance Sampling. Today, there are many smart edge devices such as smartphones, AR/VR headsets, smart speakers, robots, drones, as well as the massive amount of data they generate on a daily basis. As AI chipsets emerge, the majority of edge devices will be equipped with machine intelligence powered by deep learning to not only perform on-device inferences, but also collaboratively train a deep learning model from the on-device data collected by themselves. Edge devices are connected by wireless network. Therefore, unlike data center setting, on-device distributed training only has limited bandwidth, which leads to longer training time. Existing solutions are focused on improving the training efficiency for centralized clusters. However, it falls short when shifting to edge or mobile environments. Existing solutions are the first approach is the gradient compression. By compressing the gradient, it can reduce the amount of data to be transferred and then reducing the communication time. However, these methods only work after the training is close to convergence or may lose accuracy if compression rate is too large. The second approach is called local SGD, where the clients perform multiple local updates before sending the gradients for aggregations. However, it may deviate from the global optimal model when multiple local steps are performed. The final approach is called overlapping. The idea is to overlap the communication with gradient computation. But it does not work well under mobile environment because communication time is significantly larger than the gradient computation time. So different from previous approaches, Mercury aims at improving the training efficiency to reduce the number of iterations for convergence. The total training time is approximately equal to the number of iterations times per iteration time, which is the sum of computation time and communication time. The idea of Mercury is to focus on training important samples, and by doing so, we can reduce the number of iterations required to converge. More importantly, Mercury is a general framework that can also be applied to a federated learning setting. To do so, we use a very well-known technique called importance sampling. Here is one example. The color of a data point indicates its importance. The darker it is, the more important it is. So using random sampling, we may sample a mini batch with few important samples, contributing less to training. However, if we have a distribution that represents the importance of data points and sample the data using this distribution, the generated mini batch could contain more important samples, helping the training to converge. Using importance sampling in SGD training is based on an assumption. Training data have different importance. So is this true in real world? To see this, we plot the distribution of sample losses, which can be viewed as the indicators of sample importance. We can see that at early steps, the sample losses follow Gaussian distribution. After about 1,000 iterations, most of the samples have small losses or near zero losses. Only a small number of samples have large losses. That being said, if we adopt random sampling, most of the SGD training will be wasted on learning samples that do not contribute to convergence. To implement importance sampling on distributed SGD training, it seems very straightforward if we just replace random sampling with importance sampling. However, there are 3 challenges when we implement this. The first challenge is how do we get the importance of all the data points in each iteration? We can use the loss of sample as its importance, as I mentioned before, which means before generating a mini batch, we need to compute the losses for all the on-device data using feed-forward process. Consequently, the overhead of applying importance sampling in training is very large, overshadowing the benefit it brings. To address this challenge, we propose group-wise importance sampling. The idea is to divide the samples into groups and only update the importance distribution for one group each time. For other groups that are not updated, we use the cache importance distributions. As a result, we do not need to update all data points at once and reduces the cost. The second challenge is that the importance distribution is computed by each device for its local data. So the importance distribution only represents the local importance at each device. However, it is problematic if the data importance is imbalanced across different devices. For example, a device may collect many important or hard samples, while another device collects many easy samples. This biasness will lead to low efficiency in importance sampling. To address this challenge, we propose importance-aware resharding, which shuffles data samples across devices. By exchanging the data between clients, the imbalance of importance distribution will be mitigated. However, as the bandwidth is limited in mobile environments, we cannot afford to exchange all data. Mercury only exchanges important data, as these data have higher chance of being selected for training when using group-wise importance sampling. As a result, we can achieve resharding with less communication cost. The final challenge is that the training will be inefficient if we implement group-wise importance sampling and importance-aware resharding sequentially. As shown, the importance computation and data resharding is sequentially inserted in the original training process, incurring unnecessary blocking and overhead. Mercury incorporates a bandwidth adaptive computation communication scheduler, which schedules the execution of importance computation and data resharding in parallel in a bandwidth adaptive manner to reduce overhead. Specifically, since the gradient aggregation only uses network resources and the gradient computation only uses compute resources, the group-wise important computation and importance-aware data resharding can be overlapped with gradient aggregation and gradient computation, respectively, and they can be both executed in parallel. Here is the conceptual comparison between rudimentary importance-based framework and Mercury. Here is the detailed system architecture of Mercury. We conduct experiments on 6 public data sets for image classification, speech recognition, and natural language processing tasks. We compare Mercury with 2 baselines. The first one is called TIC-TAC, which is a state-of-the-art distributed deep learning training framework that uses overlapping technique. The second one is called ADACOM, which is a distributed training framework using local SGD technique. This figure shows the overall performance under different bandwidths. We show the speed up over standard SGD approach. As we can see, Mercury achieves highest speed up across all data sets under different bandwidths. We also evaluate the effectiveness of the proposed group-wise importance sampling. We compare it against the all-inclusive importance sampling strategy, which recomputes the importance of every sample in the local data set at each SGD iteration. We can see that while group-wise importance sampling uses 20% more iterations to converge, it is actually 4.2 times faster than all-inclusive strategy when translated into local training time. In this experiment, we compare the performance of proposed importance-aware resharding to importance-agnostic resharding. We observe that compared to non-resharding, data resharding is able to boost the accuracy by about 1.8%, demonstrating the need of data resharding for achieving state-of-the-art test accuracy. Second, the proposed importance-aware strategy is able to converge to the same test accuracy with only about half of the data transfer amount. We also evaluate the contribution of BACC scheduler. We can see that although BACC uses 5% more iterations to converge, when translated into total training time, it is 55% faster than the sequential pipeline. It indicates that by using BACC scheduler, we are able to properly schedule the execution of group-wise importance computation to achieve higher network and compute resource utilization. We also investigate the scalability of performance of Mercury. When scaling from 4 devices to 8 and 12 devices, Mercury gracefully maintains the speed up over standard SGD under various bandwidth availability. This result demonstrates that Mercury is able to maintain its performance when the number of edge devices scaled up. Lastly, we investigate the effectiveness of group-wise importance sampling when the devices have non-IID data. We generate 3 non-IID Cipher-10 datasets using dish-laid distributions with 3 different concentration parameters. Alpha. The smaller alpha is, the higher non-IIDness the dataset is. We observed that group-wise importance sampling is able to increase training efficiency, achieving 2.7, 2.5, and 2.4 speedups over a random sampling. This indicates that Mercury is still effective when the data set is non-RID distributed across devices. In this work, we present Mercury, a distributed framework that enables efficient on-device training without compromising the accuracy of trained models. Mercury addresses the key bottleneck of on-device distributed training using group-wise importance sampling, importance-aware resharding, and the BACC scheduler. Experiments show that Mercury not only consistently outperforms the state-of-the-art approaches, but also achieves speed up under federated learning setting. Future work includes extending Mercury to support other deep learning applications. We believe Mercury represents a significant contribution to making on-device distributed training practically useful in real-world deployments. Thank you, and I'm ready to take questions.
Thank you very much. We gained some time, so are there any questions in the room? Okay.
Thank you for the nice talk. So I'm a little bit confused about what's the definition of importance that you use in the first slides. So how do you say sample is important?
Yeah, so the first slide, yeah, we can use this slide. So here, as we can, yeah, so here we use sample loss as the importance of the sample. So if you put a sample into the deep learning network and get its loss, if the loss is larger, which means it can contribute to more to the training, and then it is more important.
And this is over all samples, right? These histograms. So if a sample is fed to the network, as you can see here, beginning of the training, that might be very hard for the network. However, if it is fed to the later phases of the training, that might be simpler, right? So this is not fixed. Based on training trajectory, we know that a sample is hard or simple.
Yeah, correct. The importance of the samples changes as the training goes. So at first, it's Gaussian distribution. You can see that most of the training samples are neither hard or easy.
Simple. Mm-hmm.
Yeah.
So later, when you train a network, can you make an example? Like I have a CFAR10 over VGG, let's say, I train it, and then after training, you know that which samples are more important or less important, and this is your importance.
Yeah, after training, you can tell which sample are more important. And
okay,
then
so you train a network and use this as a label for the importance of the samples.
No, the importance of the sample are calculated on the fly. So after you train, you get a mini batch, and then you put it into the network for one iteration training. And then for the next step, you can get a new sample distribution loss.
Okay, this is dynamically changing over the training, right? So for
Correct.
each batch, you have another score. Okay, that's now. Okay, I got it. Thank you.
Yeah, thank you.
Thank you very much. Any more questions in the Slack channel? No questions. So thank you, Xiao Zheng. Let's thank.
Thank you.
And we can move on to our fourth and last speaker of the session, which is Eng Lee. Paper 4. Okay, the fourth paper is FedMask, Joint Computation and Communication Efficient Personalized Federated Learning via Heterogeneous Masking. Ang Lee is a fourth-year PhD student working with Professor Yaran Chen at Duke University. His research primarily focuses on federated learning, mobile and edge computing, and privacy. So, Ang Lee, we are ready. Go ahead. Thank you.
Okay, thank you for the chair for the introduction. And hi, everyone. My name is Ang Lee. I'm a first-year PhD student from Duke University. I'm working with Professor Yiran Chen. And today I'm going to present our joint work with Michigan State University. And the title of our work is FedMask, Joint Computation and Communication Efficient Personalized Fed Learning via heterogeneous masking. So for today's presentation, I will first briefly introduce the background of Fed learning and the motivation of our work, and followed by the design of FedMask. And I will then show the experiment and the key results. Finally, I will briefly conclude and summarize our work. So the era of edge computing has arrived. So billions of edge devices have been deployed in the real world, such as smartphones, robotics, AR/VR headsets, drones, and autonomous cars, etc. Those devices are constantly generating a huge amount of data at the network edge. So artificial intelligence, especially the deep learning technique, has been widely applied into many applications and achieved great success. So it's a natural choice to employ AI to realize the edge intelligence, to unleash the potential of the data at the network edge. So given the different types of information gathered by the edge devices, so AI can help to boost many intelligent applications on device, such as object detection, voice recognition, and many other AI-based applications. So the conventional solution to realize the edge intelligence requires edge devices to offload the data to a server, and then a centralized training is performed on that server. So unfortunately, such a centralized training method raises serious privacy concerns due to the data offloading. So Fed learning is an emerging distributed machine learning paradigm that is able to effectively address the privacy issue. In Fed learning, a set of devices will sample to participate in each communication round for training. The device will randomly sample a mini batch from the local data, and then apply the optimization algorithm, for example, SGD, to compute the local updates. Then each device will transmit the local updates to a central server. The server will perform aggregation on the local updates and update the global model accordingly. But finally, the updated model will be sent back to each device for continuous training. Because only the local updates are communicated between devices and the server, so no local data will be explicitly shared. However, when we deploy the Fed learning in practice, we still come to several critical challenges. The first challenge is data heterogeneity. The data heterogeneity by edge devices the data generated by edge devices is often heterogeneous across the devices. Such data heterogeneity makes it difficult to train a shared global model that can be well generalized for all devices. Therefore, personalization becomes necessary to handle the challenges posed by the data heterogeneity. In addition, communication cost is another key bottleneck for Fed learning due to the limited or expensive communication resources. Although existing method like a LG Fed average has improved the communication efficiency, it's not significant enough because the communication cost is still too high to be affordable for edge devices. So besides communication cost, computation cost is another critical challenge for further learning. There's a trade-off between computation and the communication cost. In particular, at the bottom right figure shows, the performing more local epochs requires more local computation efforts, but reduce communication cost. However, a larger number of local epochs may lead to the divergence between local objective of each device and the global objective. However, the optimal number of local training epochs is a task dependent, and we need to train this hyperparameter based on the specific learning task. In addition, deploying the resource demanding DNA models, which is learned through the further learning on resource constrained edge devices, is also technically challenging. So it's necessary to improve both training and inference computation efficiency on device. To tackle those challenges, we propose feathered mask, a novel further learning framework that can jointly improve the communication and the computation efficiency of personalized further learning in a unified manner. And given a variety of mobile devices and associated heterogeneous data, feathered mask enables each device to learn a personalized and sparse deep neural network. Such a model can run efficiently on edge devices and can be deployed for efficient mobile deep learning applications. So next, I will present the design of feathered mask. So in this work, as we mentioned, we propose feathered mask that can simultaneously minimize the communication cost, reduce the computation cost for both training and inference, and learn a personalized model for each device to mitigate the data heterogeneity. The key of feathered mask is to enable each device to learn a heterogeneous and structure sparse the binary mask rather than directly optimizing the local model parameters in each communication round. So each device will communicate the binary mask only, and once the training of the binary mask is finished, the heterogeneous binary mask of each device will be element-wise applied to the frozen local model to generate the personalized model. So let's see how the feathered mask works. So at the initialization stage, the central server will randomly initialize the heterogeneous data. So each device learns a heterogeneous binary mask via the proposed one-shot pruning method. I will elaborate the pruning method later on. And in each communication round, a set of devices is randomly selected to participate in the feathered learning. Instead of optimizing the local model parameters in feathered mask, each device optimizes the binary mask with a structured sparsity regularization while freezing the parameters of the local model. As such, only the binary masks are transmitted from the devices to the central server. So as only one bit is used for each element in the binary mask, so the communication cost can be dramatically reduced compared to transferring the real value, the floating value local model parameters. The central server performs the aggregations on the received binary masks. The aggregation strategy is specifically designed such that only the elements are overlapped across devices are aggregated, while keeping non-overlapping elements unchanged. In doing so, the personalization of the binary mask is preserved and updated binary masks will be sent back to each device. So finally, the binary mask will be element-wise applied to the frozen parameters to generate a personalized and the structure sparse model. Since performing the feed-forward and the backup propagation computation over the structure sparse model is much more efficient. It's much more efficient compared to the original dense model. The computation efficiency for both training and the inference is significantly improved as well. So, however, to realize such a complicated design, we still come to several critical challenges. So, number one, how to jointly improve the communication and the computation efficiency. Number two, we need to answer how to incorporate the personalization for each device. And number three, we need to figure out how to aggregate heterogeneous binary masks on the central server while preserving the personalization. We will answer those challenges one by one. So before we diving into the details of the fed mask design, let me first introduce the binary mask optimization. As learning the binary mask is the cornerstone of the whole framework. So yeah, we let's first discuss how we can optimize the binary mask. So given the model fixed, we freeze the model parameters. So we can apply a binary mask to the fixed weights for generating the model to perform the inference. However, it's technically infeasible to apply existing optimization algorithm like a SGD to optimize the mask due to its binary value. Therefore, we introduced real value the mask MR to facilitate the mask optimization. In the feed-forward step, the real value mask MR is binarized to the M, the binary mask, using the threshold function. In the back propagation step, the gradients of the binary mask M can be calculated using the equation tool here. But the threshold function is non-differentiable, and directly copying the gradients of M to MR will result in a huge gradient scale variance. So we incorporate a sigmoid function to approximate the binarization from MR to M during local training. By introducing the differentiable sigmoid function instead of the hard threshold function, the gradients of M can be successfully back propagated to the MR. So to jointly improve the communication and the computation efficiency while incorporating the personalization for each device, the key is to learn heterogeneous and structure sparse the binary mask on each device. The first step of fed mask is to learn a heterogeneous binary mask from each device using each device's local data at the initialization stage. Since the gradients of real valued masks are directly scaled by the values of the fixed parameters, using only the magnitude of the real value mask is not a fair metric for pruning. Therefore, we designed the one-shot pruning method based on the combination of real valued mask and the fixed parameters. In addition, each device preserves the denser structure of the top layers because in most cases, the top layers works for the feature extraction, and we only prune the last several layers, which compose the classifier part in the one-shot pruning phase. And after performing the one-shot pruning at the initialization stage, each device obtains a heterogeneous mask and can start to perform local mask optimization in each communication round. In particular, in each round of fed learning, each device iteratively optimizes the binary mask using local data while keeping local model parameters frozen. To improve computation efficiency on device in a hardware-friendly way, we employ the structure sparsity regularization during mask optimization to learn binary masks while with the structure sparsity. When designing the aggregation strategy, our goal is to maximally retain the personalized information in heterogeneous binary masks. To achieve this goal, we propose a mask aggregation scheme where each element in binary masks is aggregated independently. As the left figure shows, the central server only performs the averaging aggregation on elements that appear in 2 or more binary masks. Then the central server updates these elements in corresponding binary masks using as an aggregated value. For the elements that are not shared across binary masks, the central server keeps them unchanged without performing aggregation. And finally, the updated binary masks with preserved heterogeneous structure will be sent back to the devices accordingly. As a final step, as illustrated in the right figure, once the training of the binary mask is finished, the heterogeneous binary mask of each device will be element-wise applied to the frozen local model to generate the personalized model. In addition to addressing the data heterogeneity, the heterogeneous binary mask result in a more sparse local model such that both the communication and the computation costs can be further reduced. Next, I will show the experiment and the result. To demonstrate the generality of fed mask across applications, we apply fed mask to build 3 representative mobile AI applications using 4 benchmarking datasets, including image data like EMNIST CFR10, sensor data like human activity recognition, HAR, and the text data on the Shakespeare dataset. And all the datasets are partitioned in a 9D manner, and we implement and evaluate these applications on various edge devices like NVIDIA Jetson TX2 and Jetson Nano Raspberry Pi. To comprehensively evaluate the performance of fed mask, we compare fed mask with 6 baselines. We apply the same base model configuration and the training settings to each baseline method as a fed mask. In addition, we evaluate both training and the runtime performance of fed mask using 2 sets of metrics. We use inference accuracy, communication cost, and computation cost to evaluate the training performance. Memory footprint, inference time, and energy consumption are used to evaluate the runtime performance. First, we compare the fed mask with the baselines in terms of the accuracy communication trade-off. As the left figure shows, the red star represents fed mask. We can see fed mask is able to achieve a large gain in inference accuracy with a significant reduction on communication cost. So although standalone method doesn't pay for any communication cost because this method only performs the local training on the local data, and fed mask shows substantially better performance compared to the standalone due to leveraging all the local data rather than training the model using only limited samples on device. So in addition, compared to the BN fed average, which is measured by combining the binary neural network with fed average, so this method also transmits binary parameters between devices and the server. So fed mask doesn't significantly outperform being fed average on communication efficiency. However, fed mask considerably increase the inference accuracy compared to the being fed average. So the top right figure shows a comparison of computation cost between fed mask and the baselines. Due to the structural sparsity, fed mask is more computation efficient in all the applications compared to the baselines. So moreover, we also perform evaluations on different parameters. For example, we evaluated the impact of the number of participating devices in each communication round. As a bottom right figure shows, the inference accuracies will slightly increase with a larger number of participating devices in each communication round. And we also perform the runtime performance evaluations. The results here show FedMask can achieve significant reduction on memory footprint, inference speed up, and energy consumptions compared to the baseline method. So these benefits come from the structure sparsity of the personalized model on device. So to conclude, in FedMask, devices learn and communicate the heterogeneous binary masks rather than directly optimizing local model parameters. The aggregation strategy is carefully designed to independently process each element in a binary mask, such that the personalization of the masks can be preserved. Our experiment demonstrated that FedMask can significantly improve both communication and the computation efficiency at the same time. So that's all of my presentation. Thank you so much. I will be happy to take your question.
Thank you very much. We are right on time. Are there any questions? So we can spare some minutes. Are there any questions for Ang Lee? The room.
Do we have time?
Yes.
Okay. So can you please go to slide 14 with challenge 3? Yes. So I'm not sure if I got it right. How do you do this challenge 3? How do you come up with the solution? Because you have different sparse networks. How this aggregation works again? Please?
Yes. The goal of the aggregation is try to maximally maintain the personalization the heterogeneous structure of the binary mask for each device. So as the left figure shows, here we show one toy example given 2 devices and a layer of the mask, and we can see.
I guess we can also see your mouse. Maybe you can walk me through because I'm lost.
Yeah,
sure.
You're
referring to.
Can you see my mouse here?
No, not actually. This is not Zoom.
Oh, okay.
Yeah, okay.
But I can just describe it. So as we can see here, we have device I and the device J, and we can see the channel 1 and the channel 1 on device I and the device J is overlapped because after the pruning, the mask of the channel 1 is still preserved. It's still maintained. So the server will perform the aggregation over the channel 1 between the device I and the device J. But for the channel 3, we can see it only appears on the device I. So the server will not touch it. So we will keep the values in the channel 3 unchanged.
So this is an XOR, right? So whatever is similar between these 2 networks doesn't change, and then the other keeps the rest, right?
Yeah.
So, okay.
Yeah, that's right.
Okay, thank you. And then 13, can you go to 13? What was the sparsity? So it's a L1 lasso regularization.
Right. Yeah, we use group lasso, the regularization for the structure sparsity regularization.
Okay, and my last question is that, correct me if I'm wrong, but the whole, like the main contribution is that the communication, and that's because you exchange the binary mask instead of weights, right? So you don't need to.
Yeah.
You don't need to transfer the whole weights, but only a binary mask, which is bytes in terms of.
Right. We can see it because we only learn and transmit the binary mask. I think we can improve both communication and the computation efficiency at the same time.
Okay, cool. Thank you. That was a very nice work.
Yes, thank you so much.
One question in the Slack channel.
Yeah.
Okay. There's here Tianai Zheng, I think. He has a question. He asks how to define heterogeneity. And it says in his understanding, it means that the device collects data from different formats, but in the evaluation, it seems like you are using homogeneous data sets.
Yes. So in our experiment, we only actually there are many ways to to capture the characteristics of the NID. For example, like the label skewing or quantity skewing or even feature space variations. So in our case, we considering the heterogeneity caused by the label skewing, because in our in the benchmarking data set, we partition the data set in the 90 manner. For example, we only allow each device we only allow each device hold 2 classes of data, so we can simulate a heterogeneous environment.
Okay, thank you. No more questions. So let's thank Angli. Thank you very much.
Thank you.
So it's time for a break, lunch break. It's in the same place as the coffee break. So feel free to go. Thank you.
So yeah, it's like hopefully it doesn't go to this. I don't. With a camera that is oh, that's
Yeah, wow.
Okay. Oh, doesn't have to go near. Sounds good. All right, let me try share my screen.
How do you say your second name?
Kiagadi in Persian. Kiagadi, but you can say Kiagadi. Kiagadi is totally fine. Everyone's saying Kiagadi, so that's fine.
Okay, we are
Let me.
So I think you did.
Oh yeah, that's good. Okay. Let me actually remove this. Oh, you guys don't see. Okay, never mind. Anyway, okay, that's fine. All right, thank you so much.
Perfect.
All right.
Yes, we'll see you in a bit.
Yeah.
the conference. Yeah, 2 hours. You know where the lunch is? Yeah, I just want to go to one for
It's 20 minutes to, so 16 minutes for your talk. No, Andrew. There you go. Yes. So I told them that they can connect to Zoom. Yeah. If they can just share the screen. Yeah, and see themselves and that's it. Exactly. That's it. To the Zoom. Yeah. Okay. Yeah. I mean, this is Spanish, but you understand. That's fine. I'll speak English or Portuguese. Yeah. This mic is fine? Yeah, this mic is always on. Connected. Okay. So if somebody from the public needs to make a question, yeah, perhaps me or Manuela is going to pass the microphone. So you just need to be there by. Okay. So do you want me to sit there? Yeah, wherever you. Because I was gonna sit here and let them talk. Okay. And I'll present them through this mic. Actually, you should be better. Through this mic. Okay, so yes, you're going to be here first. You're the part. He's the first one. You're the first. Yeah. Okay. Perhaps one is next. Say all of them. So yeah, you can here. Yeah. So what do we present seconds again? Actually, I don't know if he has to put presentation here. We talked to someone who was here before last week. Yes, yeah, I think. And that's okay because he said the issue before was the sound. And now it's okay. So yeah, you connect to the Zoom meeting. Yeah, and you share the screen and you like yeah, that's it. Yeah. Okay. And so, and this is showing the Zoom meeting or this screen. Right now we are sharing that screen. But right now I will. You control this. So I just put here. Oh, this is okay. I don't know if you have like a piece of paper to enjoy. If you have any questions, where? By the way, thank you. Yeah, maybe that's one for real. But none of you guys are. So you can share this one? You can share because you are sharing.
Hello.
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 Hi, Przemysław, can you hear us and see us?
Yes, I can hear you. Hello.
Perfect.
Can you guys
Now,
hear?
you're going to be the second presenter.
Yes.
Ali's going to be first.
Mhm.
So
Perfect. So I can share my slides, right?
just a second. We're setting up Ali, and you'll go right after, and they will give you permissions to share.
Perfect.
share
Okay.
your
So I
screen.
don't have to send you the PowerPoint presentation to.
No, you don't have to. You just have to share your screen.
Perfect. Okay. Perfect. Thank you so much. Okay. Thank you.
That's it.
Okay. So I'll disconnect. So just to not bother you. Okay. So talk to you soon.
Sure. I'll present when I present you. You just share your screen and you go ahead. Okay.
Perfect. Perfect. Thank you. Thank you.
Thank you. Bye.
E aí terá de ser o João a fazer um bocado a ponte. Sim, a dizer, está aqui alguém no Slack que está a perguntar isto assim. before yeah. Well, at least I think. Yeah, so we start. Yeah. So I see. Hi, everyone. My name is João Diogo Falcão, and I'm your session chair for the journal track 1. We're going to have 4 presentations, and I have here with me Ali Kiahadi. He's a 5th year electrical engineering PhD student at the University of Massachusetts Amherst under the supervision of Professor Deepak Kanizan. His research includes system design for unobtrusive physical and physiological sensing of humans, which can be broken down to design and implementation of sensors, electronic boards, digital signal processing pipeline, and vertical integration of these layers. He has received his Master's of Science degree from Bogazici University in Istanbul and his Bachelor of Science degree from the University of Tehran, both in electrical engineering. Welcome.
Thank you very much for the introduction. Hello, everyone. Welcome. My name is Ali Kiavadi, and I'm going to talk about my work, continuous measurements of interactions with the physical world with a wrist-worn backscatter reader. This work is a result of the collaboration with my colleagues Panhu, Professor Jeremy Gomison, Soharu Snaminia, and my advisor Deepak Gomison. Human-object interaction recognition has become increasingly important to understand how people interact with different objects and how to provide feedback. A few examples include providing assistance for the elderly in their everyday tasks, for example, taking their medications. Also for the addiction domain, it's very important to monitor the users during their smoking, eating, or drinking sessions to provide just-in-time intervention. And there have been several different research approaches to tackle this problem, the most dominant of which is computer vision, where a camera is used to detect humans, the objects, and the interactions that's happening between them. However, you cannot have cameras everywhere, so this solution is limited in portability, and there's also privacy issues with cameras. And the second most popular approach is using wearable devices. Now, wearable devices, they can use IMUs or acoustics to find different interactions using the hand. But however, these approaches are typically inaccurate because they are looking for a needle in a haystack in terms of finding the exact time slot in which a specific interaction is happening. And this problem gets worse considering the fact that these approaches typically don't provide any information regarding the object that the user is interacting with. As a result, many of these interactions can be confounded with each other. A more direct approach to this problem would be to attach RFID tags on the objects of interest. As a result, we're going to need somehow to read these tags, which is the RFID reader. The RFID readers are typically bulky and power-hungry elements, which means they're often infrastructure mounted, which again limits their portability and coverage zone. The aim of this project is to design and implement a wearable low-power RFID reader. We propose attaching such an RFID reader on users' wrists or embed them in their smartwatches, and attach a RFID tag on the objects of interest. As a result, we can now recognize the objects, but there are several challenges in actually determining tracking the interaction while designing a low power and small form factor system that can only sense the objects around the reader. Now, to understand and solve these challenges, let's take a look at the basics of RFID reader principles. The RFID readers works by shining an RF wave onto an RFID tag, and the RFID tag responds back by modulating its baseband information on top of the amplitude or the phase of the received signal and reflecting it back to the reader. As a result of this passive nature of the RFID tag, the reflected signal is orders of magnitude weaker than the initial RF wave. Here we can see the basic block diagram of most typical off-the-shelf RFID readers. The baseband signal is mixed with the local oscillator signal passing through a power amplifier to get amplified and routed toward the antenna. Typically, the same antenna is used to route the received signal toward the RX chain, which consists of self-interference cancellation blocks, low noise amplifiers, and phase shifters to provide in-phase and quadrature signals. Now, this table summarizes the characteristics of the off-the-shelf reader with the goals that we have in our minds. Now, the 300 milliamp hour battery is just an example of like a coin cell, small coin cell battery that can be confined in the space of a smartwatch. Our goal is to be able to fully operate for 10 continuous hours using this small battery while providing smaller reading range. Now, the smaller read range is because we want to remove the number of tags we are reading at each time and focus on the tag only in the vicinity of the reader. The in-phase and quadrature output are essential in our work because we need to find the physical layer information of the signal to find the exact interactions happening at each time window. Now I'm going to take you step by step toward the process we took to modify the typical RFID reader design to reduce the power consumption, reduce the read range, and reduce the form factor. The first and most obvious step is to remove the power amplifier. And power amplifiers are very power hungry, and they're used in off-the-shelf readers to increase the power and definitely the read range. Next step is to remove the low noise amplifier. The low noise amplifier is used in the receiver chain to increase the sensitivity and the read range. And the next most power consuming part is the active RF self-interference cancellation. This is also very power hungry, but it's important to have the self-interference cancellation somehow in our design, which is why we replace the circulator in our design with a directional coupler. Directional coupler provides more isolation. As a result, we can have a better self-interference cancellation without the active elements. We also replaced the active phase shifter with our passive delay line, which is serpentine shaped, as you can see here. We also use a passive mixer in our design. And as a result, here is the overall receiver side design of VerID, where the transceiver transmitter side is summarized in the signal generator you can see on the top left. Now I'm going to show you the final prototype and walk you through the benchmarking of this and evaluating the system. Here is the final prototype, and which has 3 main sub-modules. The main frame, as you can see in the middle, consists of microcontroller, BLE, a Bluetooth module, and an LCD for application development purposes. The second PCB is the IQ in-phase and quadrature reader module. That's the receiver side. And the board highlighted in red is the carrier emitter module consisting of microphone as RF transceiver IC and the matching circuitry. Initially, we opted to choose to go with the flexible antennas, but due to heavy attenuation because of body adjacency and mismatching, we opted to go with the rigid PCB antenna, which outperformed the flexible antenna. The design has consumed 72 milliwatts of power while transmitting 9 dBms of output RF power. The dimensions are 42 by 42 millimeters squared, and this system is compatible with the EPC Gen 2 protocol, which I'm going to show you in a couple of slides. The read range is also around 30 centimeters, which I'm going to show you how we obtain these numbers. Now, to find the detection of range in this work, we considered 2 different methods, 2 different approaches. The first approach is to use NXP UCode 8 tag. NXP UCode 8 tag is a state of the art at the time of writing this paper in the tag RFID tags, which has a sensitivity of -23 dBm. This is as opposed to the sensitivity of the old-fashioned RFID tags. They have only around -19 dBm, which means the NXP tag can be read from a further distance. This 3D plot here is drawn by pinpointing the exact location around the reader at which the RF power passes -23 dBm. If you see the positive numbers on the y-axis, it correspond to the space in front of the user's hand where users reaches to grasp an object. As you can see, the antenna placement is tuned in a way that maximizes this number. The second method for finding the read range is actually implementing the EPC Gen 2 protocol to read more old-fashioned commercial tags. The EPC Gen 2 protocol works by having a conversation between reader and a tag that finally the tag provides the unique EPC code. And what we did in this work was to implement the query signal of this EP62 protocol in BearID, so we can draw this plot, which is the distance in 5 different directions around the reader that the tag responds to the query message of the reader. As you can see, the read range is around 25 centimeters in different directions. We also compared our design RFID reader with the off-the-shelf reader, and we chose AS3993, which was the best off-the-shelf reader at the time of writing this paper, which was considerably lower power than the other off-the-shelf readers. We compared the phase and tracking accuracy altogether with the signal-to-noise ratio in these 2 plots. As you can see, in close distances, the phase measurement accuracy doesn't really work for the off-the-shelf reader, and which might be due to the internal amplifiers and saturations in very close distances. However, after 60 centimeters, the off-the-shelf reader outperforms BearID. And same story is true for signal-to-noise ratio. In close distances, they have very similar performances, but after 60 centimeters, the off-the-shelf reader again outperforms. And this proves the fact that BearID is designed to be optimized to sense and measure these tags in the close vicinity. Now let's take a look at different interactions we are interested in and bring a sample of those and see what kind of features we can get out of them. The first interaction of interest is holding an object, which consists of grabbing, followed by duration of holding and releasing the object. As you can see, the signal strength drops when holding the object, which is due to the hand blockage. As you can see, also the phase greatly tracks the distance between the reader and the tag. The next interaction that we are interested in is passing by an object, which can be useful when you want to detect humans' movement through narrow passages like a door frame. And RSS is very useful in detecting past information. The next interaction that we studied is touching, which can be very similar to holding in physical layer information, which is why we chose different temporal features from these signals, as I'm going to show you in the next slide. For segmentation and feature extraction, here's an example of 10-second signal containing the holding action. The segmenter actually finds the peak in the RSS signal and plots a 2-second window around it, then normalizes and uses low-pass filter to find the envelope of the signal. And then it finds peaks and valleys in sub-windows inside this 2-second window. These red dots show a trend in signal strength, show a temporal trend in signal strength, which altogether with other phase-based temporal features will be fed to our classifier for a leave one subject out classification. The interactions and the measurements is this way. We ask the user to grab a soda bottle for the grab label. Then we ask them to release the same soda bottle. We place the tag on an object and we ask the user to touch the tag or around it. And we ask the user to pass by the object. We also recorded some random non-interaction as idle labels. As you can see in this confusion matrix, our SVM classifier, which is a relatively lightweight and quick classifier, can distinguish between these interactions with 85% accuracy. And the final case study we did in this project was a just-in-time smoking intervention, where we asked a user to mimic a smoking session, where the user is reached into his pockets and takes out a cigarette pack. And to consider the worst case scenario, we asked the user to use his non-instrumented hand to take out the pack. And then the user uses his instrumented hand to take out the cigarette and put it into his mouth. As you can see in this plot, at t equals 2 seconds, the initial contact is happening between the hand and the cigarette pack, and at t equals 5, the user is taking out the cigarette. And at t equals 13 seconds, the cigarette is put into mouth. This is the labels. These are the labels that BearID extracts from the signals. By the way, the signals you are seeing are the signal strength and the phase received from the physical layer information. As you can see, there are several grab, touch, and releases labels from BearID, which is due to the complexity of the interaction by itself, by its nature. As a result, we can see that where ID can perform just-in-time intervention and gives us around 7 to 8 seconds before actual smoking happens. I want to finish my talk with a conclusion. Where ID can detect the typical user's interaction with the objects of interest, and we can also be implementing EPC Gen 2 protocol to detect commercial RFID tags. Where ID is has a small form factor and consumes around 10 times lower power than off-the-shelf readers. And as a result, it can bridge the gap that happens when you are reading a tag or finding human gestures by themselves. Thank you so much for your attention, and I'll be happy to take questions.
Thank you, Ali. Any questions from the room? Let's check any questions on Slack. If nobody has a question, I have a question for you. You mentioned some of the actions like holding, passing, and touching, and you talk a lot about the range of the system. How about the resolution when there's overlapping objects with tags? Have you looked into how interfering tags would react with your system?
I see. Okay, so the good thing we have here is that each time you read a tag, you have the EPC code. Now, the EPC code distinguishes between different tags, so you can separate these interference from the EPC code. For instance, if at each time window, let's say you read 2 tags, right? But you can separate the physical layer from information based on the EPC code that you're getting from both tags. So you can technically separate out all the tags and all these traces of phase and physical layer information from each other using the EPC code that they have.
So you'd be able to tell between different objects, but would you be able to tell how far apart I would be touching them?
Well, that would be a more complex question, and not exactly. The exact distance between these requires much more, let's say, work in process, but no, that's not exactly possible.
Thank you. Thank you so much.
Yeah, thank you very much.
Last question? No. Great. So we're going to go on to the next presenter, who is presenting dynamic task-based intermittent execution for energy harvesting devices. His name is, I'm going to try and pronounce this, Przemysław Pawłowczak. He's an associate professor in the Embedded and Networked Systems Lab of Delft University of Technology. He is leading sustainable systems labs where he works with his team on small embedded battery-free intermittent power devices. Let's see if we have him online.
Yes, we do.
There you go.
Thank you.
Go ahead.
Yes, Mr. Chairman, thank you so much for the introduction. Once more, it is a great pleasure to be here, at least virtually. My name is Przemysław Pawłowczak, and I have a pleasure to present in a very succinct and compact manner what dynamic task-based intermittent execution for energy harvesting devices is. This work has been prepared together with a team of colleagues, Amjad Youssef Majid, Carlo Delladonna, Kiwan Mank, Alexei Colin, Kasim Sinaniririm, and Brandon Lucia, and me. This particular work that I'm presenting today has been published at ACM Transactional Sensor Networks in February 2020. The link to the presentation is provided on the slide itself, and I'm pretty sure it's already provided at the website of Sensys Conference. Before I'm going to start with the presentation, I'd like to emphasize that all the code related to the topic of that presentation is provided as an open source code at github.com/tudelft/tudsssl/koala. TUDSSL is a link to my lab website with other projects related to the generic topic of battery-free computing is provided. So I would encourage and ask everyone to download the code, run it, and experiment and provide comments and find issues or bugs in the code itself, because this project is supposed to be growing and be developed. Yeah? Let's start with the macro view of why this work is actually started. We have a battery problem as a community of people working in embedded systems. The batteries are big, hazardous, leaking, sometimes heavy, they take energy to recycle, they are polluting the environment, and the list goes on. There are, of course, a lot of advantages of having batteries connecting to the embedded system, providing the energy, making the embedded systems mobile. They're making embedded systems free from being powered through a power socket. But there are so many of embedded devices around us at the moment. You can pick any projection on the future of IoT. You're going to hear about billions and billions of IoT devices polluting our planet. And with each and every single IoT device, we have a battery mostly associated with it. So this electronics needs to be recycled, and the electronics of the IoT device for recycled equals the battery needs to be recycled as well. So of course, the battery technology is improving. The battery is becoming better with every single day. However, please don't expect that that in the upcoming years, a big revolutionary battery technology will happen. It will change completely the landscape of how we're dealing with the old batteries, how to replace them, and how to make the batteries last longer. Whenever I'm giving a pitch on the concept of a problem of batteries, I'm referring to an old example that I heard a couple of years ago, that at Schiphol Airport, the biggest airport of the Netherlands, one company providing localization services for passengers based on Bluetooth beacon technology. In that particular company, there was one person responsible only for going on a daily basis through the whole Schiphol airport and checking for battery problems with all the beacons. So there's a strict labor code also associated with the battery itself. So of course, for every problem, there's supposed to be a solution. And the solution to the battery problem is composed of two components: energy harvesting and a capacitor as a replacement for the battery. Since this pitch is given to the community of experts in embedded systems, I'm not going to dwell upon what energy harvesting, what technologies are there to are used to provide energy from the ambience. One of them is, of course, solar energy, and I mean the most of the energy that's surrounding us on the planet comes from sun radiation. So a simple small solar panel connected to the embedded device, together with a capacitor which replaces the battery, is already a step in the right direction, at least reducing the amount of components or necessary elements for battery to be built to reduce. Well, no simple set than done, but with every solution to a certain problems come specific challenges. And the biggest challenge related to the combination of energy harvesting and capacitor or supercapacitor as an energy replacement is the intermittent supply problem. When we as designers of embedded system don't have a direct energy storage that could store the energy at the device to be used in the future, we can only use that energy as it is. And capacitor has its certain amount of storage that is much more limited than battery itself. So at some point, the capacitor is going to deplete from its energy completely, making the device completely turning off. And this process will continue. As long as the energy is depleted, then the energy comes in, then the capacitor is being charged, then the capacitor turns on the energy supply to the embedded device, then the device performs in the computation on the device itself, system discharges, powers itself off, and the process continues. Depending on amount of energy is provided to the system, we will be able to minimize the times in between power off periods. We might be able to also increase the duration of the on time with the size of the capacitor. There are some architectures of battery-free systems which provide a cascaded architecture for capacitors, depending on what tasks are being used. These capacitors can be switched automatically from smaller to larger. Nonetheless, the problem of intermittent power supply holds. which means that without a certain architecture, and I mean by this software and hardware architecture that will provide a guarantee on execution of the computation, system based on capacitors and energy harvesting will never be able to guarantee forward progress in the computation. So for this case, we need some form of mix of volatile and non-volatile memory, for which the system will be able to, at certain predefined periods of time, store the state of computation in the non-volatile memory, and then when the energy goes back, restore the energy from the non-volatile memory back to the volatile memory and continue execution from the last moment the system has stopped. But this causes a certain problem, and this problem is provided here in this very simple code snippet. One of the ways to design software for such systems beyond providing a checkpoint is to compose the input code of the embedded device in the so-called tasks. Tasks are complete parts of the code with a predefined input and output, in which the computation can be interrupted at any point of time, and only if the device reached the end of the task. In that case, the task will be able to pass, let's say, the virtual token to the next task to continue the process. In between, the system needs to checkpoint. So within, unless the checkpoints are provided in the predefined locations, the system won't be able to restore from the computation successfully. So let's look at these two examples for the non-taskified system, in which you have a very simple loop, for which with every iteration of the loop, one variable is being increased by 1. On the left-hand side, we have a system which operates on a continuous power. On the right-hand side, you have a system which operates intermittently. So the system can stop at any point of time. So if you look at the example of the case when the power fails right at the line number 5, and at the line number 4, a system checkpointed its state. So what happens? Then in this case, we're restoring our system from the last moment of a checkpoint. In this case, this is line number 4. But what happens here is that we have stopped right after checkpoint, and in this case, variable I has increased by 1. We restore from our system from line number 4, but we don't restore from a point in which the variable should be 0. We restore from variable number 1, which means that we have, in the background, incorrectly increased the value of the of this variable by 1, causing in this case a long-term incorrect execution of the program. So one way to solve that problem is, like I mentioned before, is to not using the checkpoints at all, but providing the sort of semantics in which the code is divided into small pieces of code, which call them tasks. And these tasks are communicating with each other by the inputs and outputs. And only if the certain task has reached to the end of the execution, then the system is being checkpointed. And from that moment, the system resumes from the operation and continues tasks one by one. Well, the problem with the tasks, at least at the time that we're preparing this work, and almost 3 years ago, that the tasks were statically defined. So the programmer had to define how long the task is, when is the beginning of the task, when is the end of the task. But the consequence of that fact is that the size of the task will be completely oblivious to the energy conditions of the system. If the energy is very dynamic, so the amount of interrupts is very frequent, the natural thing is to make the task as short as possible to guarantee the code execution, even at the short periods of time. On the opposite side, when the exergy is quite stable and not that infrequently powering off, then it makes really no sense to divide this input code in a very small task, because we have a huge overhead of the re-execution of checkpointing and the restoration of the tasks. So the ideas of the Koala is to provide a system which will divide this task on the fly into smaller or larger tasks depending on the energy condition. So the main idea is that the tasks shrink and grow depending on the energy condition. So this is provided conceptually in this figure, when we have on the top hand side a conventional system with a small static tasks, And on the bottom, we have our system Koala. So looking from the left to the right-hand side, we have tasks T1, T2, and T3, which are interspersed by commit operations. So the commits state from non-volatile into non-volatile energy. So system works as it goes until the power failure happens. And this power failure happens under task of HT3. So the system needs to, at some point, re-execute the task from the last point that happened. So basically restarting the system again. When a call as task, what we do, we postponing the operation of the commit to the later stage, making the duration of the gaps in between tasks shorter, indeed reducing the probability that the power failure will affect a certain task. On the opposite side, when you have a large static task and a power failure happens, what Koala does is splits the task into shorter periods of operation, intervening in that task in a shorter duration and performing the commit operation as it goes. So that's why the advantage of Koala against the static task-based systems for intermittent power devices is that the tasks becoming automatically defined at the very beginning. From a macro point of view, the Koala architecture is composed of volatile and non-volatile memory at the end. So this is a physical memory that's connected and interacts with each other. On top of that, we have a virtual memory manager, which is composed of the page manager and address translator. I mentioned these two components later on in the description of the system, and the actual core of the Koala, which is providing the task downscaling and task coalescing. These two formal operations that are provided in the previous slide, and the application itself, which is an input statically defined by the programmer or by the compiler set of tasks. Then once compiled and loaded on the device itself, we'll be able to, through the adaptive task schedule, coalesce and downscale on the fly. In the paper, we provided 3 coalescing strategies we call energy oblivious, energy guided, and weighted energy guided coalescing. Depending on how much weight you want to provide to the dynamics of the energy system, we'll be able to more aggressively or less aggressively coalesce or downscale these tasks. I will not provide the details on these tasks because it's quite technical, and once again refer to the paper by itself. But one thing to mention how the system works in practice is that to demonstrate how the downscaling works. So in the case when the task is too large for the energy buffer or energy budget for the task itself, the Koala will at a certain point in time provided commit operation, we're going to shrink it further and further and further until it provides that the amount of lost task is short enough to fill in with the minimal energy budget, which is observed by the embedded system itself. Once again, how this works in practice, it's provided in the paper itself. The scientific insight beyond the architectural insight on how the Koala works is the introduction of new types of write after read dependency, which is very reason why the software system for intermittent power devices are provided, is the so-called task coalescing induced write after read dependency. So looking at this example, if you have 3 tasks that you want to coalesce into one, each of these tasks is composed of single operation. Addition of one variable where each of the tasks are manipulating variables that are connected with each other through the tasks. So they are independent in the sense that power of failure within each of these tasks will not have effect on the correctness of the operation. But if you will we as developers will combine these tasks into one, we're seeing that we're inducing implicitly the write after read dependency between variable X. This is the reason that Koala provides the virtual memory idea with a dedicated application programming interface in which the developer defines which of the variables within the tasks need to be write protected and read protected. Once the compiler or developer defines which these variables are, then the system is protected from coalescing induced write and read protection. Again, on the technical aspect of how this works, I refer to the slide. To conclude the presentation with one main result of the work is let's compare the Koala, our system, with at that stage state-of-the-art static task-based system called Alpaca. We have measured the performance of our Koala at the actual battery-free device, in this case, which was radio frequency powered computational RFID. The previous presentation we had today at the session talked about RFID devices. This was literally the same EPC Gen 2 protocol, but running on a battery-free domain, performing far sophisticated computational operation. The WISP itself had a 47 microfarad capacitor. We kept WISP from moving from the device, and we measured normalized runtime for 6 different benchmarks: activity recognition, AR, bit count, DC, cuckoo filter, Dijkstra, FFT algorithm, and sorting operation. 3 of these numbers, 13, 30, and 50, define different distances between a WISP and the radio frequency transmitter in centimeters. And the conclusion is that, for instance, in the fast Fourier transform, in other cases at very large distance, I wouldn't say it's a very, but a large distance from the RFID reader, Alpaca couldn't complete the computation, while Koala managed to complete the task or the benchmark successfully. In many of the cases, Alpaca is longer, performs computation longer than Koala, especially in the applications that have repeated right-of-read dependencies. But one very important thing to note is that not necessarily Koala is better than Alpaca itself. When there is no locality among access to protected variables from memory virtualization, Koala will unfortunately be slower than Alpaca itself. So Koala, in a sense, generates in all of the cases we measured successful guarantee, but that's not always necessary better and faster computation compared to state-of-the-art. So to conclude with a very short and crispy takeaway message is that dynamic task sizing makes battery systems harvesting process independent. That's it from me. Thank you so much. If someone have any comments or would like to share some thoughts beyond that session, I do look forward to your emails. I'm accessible through p.pavelchak@udelft.nl. Thank you so much for listening to my talk, and I look forward to your questions if there are any.
Thank you so much. This is very interesting work. Turn to the audience if there's any questions. If you can. Yeah, there's a question here.
Hi, Shami. I have a question regarding your assumptions of when a power failure can happen. In my opinion, it's when something is not dimensioned properly. Would you agree that it's easy to avoid power failures within the middle of a task if you just wait to have enough energy to complete the task?
That is true. That's a very good point indeed. But then you have you need to have an extra hardware to measure that energy on the capacitor. Right? That's the trade-off that we're making here. We're trying to make the system completely oblivious to the underlying hardware physical structure of the device. Huh? That's my.
So just a comparator, though, right? Would a comparator could solve this problem?
Yes, true. But the comparator also costs some energy to run, right? So.
We're talking about nanowatts, though, right? We're talking about nanowatts, which is significantly less than the usual sleep modes for most microcontrollers or most sensing devices.
I don't have the exact numbers with me, but I don't think that actually comparator that's running on MSP430 is so energy efficient that you can run it at so low rates. Correct me if I'm wrong. I don't have any numbers with me right now.
All right. Okay. Thank you.
Thank you. Yeah.
Thank you. Any other questions? Let's take a look at Slack. No, let's thank the presenter.
Thank you so much.
I want to remind the presenters that you have 16 minutes to present and there's 4 minutes for questions.
Sorry, if there's no more questions, maybe I can ask a second one. So,
2 more minutes.
Shami, I don't know if you saw the keynote this morning from Luca Mottula. I wanted to get your thoughts on how we can maybe standardize a way in which we can, test many different batteryless systems and architectures and have a way in which we can compare more fairly between different systems and different configurations, and different transistors. So what are your thoughts on this?
That's a very good point. I'm on a quest of actually trying to reach that goal. And one way to do it is to, at least the first step is to release all the source code of all the implementations that are on the market. That's one. Second is to keep all the hardware designs of all the platforms also open source. One anecdote, we're working on another project in which I'm trying to replicate results that are run on WISP 4.1, so the predecessor of WISP that we're using for Koala. There are no hardware designs online for WISP 4.1 anymore on the market. So so all the results are being generated. It will be very hard to do them right now. So that's my answer to the question. Please be open to what you do and give it to the community. So later on, someone will take it over and try to make this comparison possible. At least with my team, every project that we're running is provided on the website of my lab. That would be one thing to do. Second is to join forces. The community for this work is quite small still. So very often it makes no sense to compete. So, well, we're working with some of my colleagues on that domain. That work, for example, is a joint cooperation with Brandon Lucia from CMU. That would be a second approach to making this comparison possible. But let me just like flip the question. I'll ask you, what would be your suggestion how to make this comparison possible? Huh?
I guess for this, we'll have to take the conversation offline.
Sure,
but
I'll be happy to talk to you about it later on. So send me an email. We can talk later on. We can talk on night, and I'll be happy to share with you later on.
All right, thank you.
Thank you so much for the question, and it's a very interesting topic. We're going to move on to the next presenter, who's going to present BioSense using barometer for road traffic congestion detection and path estimation with crowdsourcing. His name is Naveen Agarwal. He's working as a professor in UIT, Punjab University, and has more than 19 years of teaching experience. He's also acting as principal investigator in the Design Innovation Center set up in Punjab University, India. He has more than 50 publications in international journals and 90 publications international and national conferences. He's a senior member of ACM and IEEE. And his areas of research include AI, information retrieval, intelligent transportation systems, and machine learning. Naveen, are you online? Naveen? We can see your screen, but we cannot hear you. And we can see your mouse moving. We can see you now. Can you try and unmute?
Yeah.
There you go. We can hear you.
Okay, so thank you for the introduction. So on behalf of all authors, so I am presenting the paper BioSense using barometer for road traffic congestion detection and path estimation with crowdsourcing. So traffic congestion, we know that it is a very serious problem and we need new ways to detect and mitigate it. And if we are able to know the routes that led to the traffic congestion segment, so this is a very vital information for all the commuters who might be going into the same direction. So if we are able to crowdsource this information, so that would help us to strategize very quickly. And that is more helpful in those developing countries where infrastructure is not available. So imagine that we get to know about these people are in a stuck state. So if we are able to disseminate this information to all the commuters who might be following the same path, so that would be very much helpful to them. So in this paper, we have proposed an unconventional method using the barometer sensor of mobile phones to detect the traffic congestion and estimate the path that actually led to the congested road segment. And we have further used the same strategy to devise two new approaches as well. So since barometer sensor is not widely used, so we have proposed a feature set to classify users' movement initially into the two categories, still and motion, and that eventually we take it to define or to detect the traffic state into three classes: moving, congestion, and stuck. And we got a good accuracy for the stuck state, which actually matters to us. Further, we have proposed a methodologies once you get in a stuck state to know that all the path which led to that stuck state. We proposed a methodology that how to look up very quickly the potential road segment on a user could be on. And approach, we have proposed an approach to estimate the recent path traveled by the user before encountering the stuck state. We have demonstrated the utility for detecting boarding and deboarding of a vehicle by the user, and also to find the occupancy rate of a vehicle. Our crowdsourcing system, we have proposed just to improve the accuracy of the whole system. And we have validated our approaches on various personal and public vehicles, on city buses, on three-wheeled auto rickshaws, along different cities and in the different countries using the multiple phones. So about barometer sensor, why we have gone through it. So it consumes very less power as compared to the other power-hungry sensors like GPS and accelerometer, which are widely used for these activities. This is barometer sensor is passive, so it doesn't get affected by the movement of the smartphones. And currently, this is a non-private sensor. We do not need a specific permission for an app to use a barometer sensor. And the roads which actually seems perfectly flat to the naked eye, actually they vary in the altitude in the different points. And that whenever the altitude is varies, so it gives a fingerprint of that particular road, which is actually different from the nearby roads in the same vicinity. And the barometer sensors which are right now in the smartphones, so they are sensitive enough to measure altitude changes up to 2 to 3 feet. And number of times this altitude changes in unit time can be mapped to the movement. We have tested this in the various settings. The barometer sensor we have tested when all windows were open and when no windows is open, in different vehicle conditions, when air conditioning is on and off, when the phone is in the bag and pocket. And we found that this is robust enough for this particular approach. So this figure presents the overall system overview. So the congestion detection algorithm that we have proposed will run on the commuter's smartphone. As soon as it detects the stuck state, so we trigger the GPS for movement and we get the current latitude, longitude of the stuck state. Then we fetch the real-time barometer reading of the last movement of the user. On the server side, we compare that using the GPS, the set of the roads on which the user could be on. And then we compare user's barometer reading with the barometer readings of the road signature we have already stored. And we propose the dynamic time warping to match real-time barometer readings to know that the path which actually have been followed by the user to reach to the stuck state. And then this information can be disseminated to the different commuters. Now the first part is the traffic congestion detection. To detect the traffic congestion, we first recognize the activity of the user, whether user in the still state or whether user in the moving. And if user in the still state, then the pressure experienced by the barometer sensor doesn't change very rapidly as compared to the user when it is in the moving state. Now, to get this information, we propose a new feature. So we now assume that the traffic never changes in a very short amount of time. We assume that the traffic state changes over a few minutes of duration from stuck to congestion and moving. That's why our feature window is about 1 minute of size. And to obtain a time series of features, we shifted this window over the time. Now, our main feature that we have proposed is we named it as a jump. So it is a difference in the altitude measure now and the 5 seconds ago. And if it is more than 1 meter, we say that we have encountered a one jump. And why 1 meter? We have actually tested on the various values. So from 0.5, 0.6, and based on the smartphone, current smartphone type of sensor, this figure can be set. Now we have tested that when we generate the jumps, number of jumps in a 120-second window, so we get these kind of pattern. So now we compare it with when user is in the still state, then the number of jumps are very less. But when user is moving, the number of jumps in the same 20-second window, which is slided over the time, the number of jumps are more. We have compared this in the various conditions, in the different vehicle conditions, and when the phone is in the bag or pocket. we can see that the patterns are clearly different from the still activity. That these patterns can say that we can now use a classifier to distinguish between the moving and the still activity. So further, we observed that the single time window cannot correctly describe the activity. So considering a window in which, say, total number of jumps, say, let's say 2, it is hardly to tell whether it is a still state or a motion. So rather than using a single time window, we use n such time windows. Suppose we get a pattern like this. So we can easily say that the user might be moving and the value 2 might be because of the some noise. So that's why we use the feature which is over the series of time windows. And we propose to use the pattern of jumps in the 10 windows. If we use the value of n to be very less, then it won't be able to capture the full motion. And if we use the value of n to be very high, then it may be capturing the more than one activities. And we have trained based on this, we have gathered data on the various vehicles and we train the classifier, the sport vector machines, and we classify and to each sample as a device being still or in a motion. So when we did this, we got a very good accuracy. We tested on a different phones and we trained on the different one phone of data and tested on another phone, trained on the mixed set of data getting from the various phones. And we got a good accuracy for this around 98%. So it means that we now know that whether the user is in a still state or moving just by using the barometer sensor. Now, this information is further clubbed to know that whether user is stuck in the traffic or not. So from various time windows, our SVM is now categorizing that whether user is in the motion or a still state. Now, in series of these time windows, our traffic congestion detection says that whether user is in the moving, congestion or stuck. And our simple road sphygmo algorithm, we named it by combining the sphygmomanometer and road, so 2 words. So if still count, if user is more still in the last 10 activities, then we say that it is a stuck state. If user is moving most of the times, we say that it is moving, and otherwise user may be in the congestion state. Now, when we compare it, the actual GPS values, now this graph shows that when we compare, we can see that there are some false cases where we have predicted wrong. And now this is the results on a Nexus 5. And similarly, when we see the results on the different phones, let's say Samsung Note 3, these phones were popular at that time when we were doing the studies. The Samsung S3, the number of false cases are more. Only the Nexus 5 gave the best results. But then we propose a new approach of crowdsourcing. So when we do the majority voting, we can reduce the number of false cases in the traffic congestion detection. And we found that using the crowdsourcing information and doing a majority voting, so this confusion matrix tells us that the actual accuracy, and we found that there is less accuracy in the congestion state, but we got a good accuracy in the stuck state. So with around about 97% of accuracy, we can say that the user is in the stuck state, which actually matters. Now, once we know that the user in the stuck state, we have to estimate the path the user might be on. So commuter may have traveled many paths to reach to this stuck state, and depending on the topography of different cities, so there could be many different ways. So our approach is, once the stuck state is there, we found the most recent batch of real-time barometer reading of moving state. And since user may be traveling in a different speed, and when we have captured the road signature, that may be at a different speed. So our time series could be of different sizes. That's why we have proposed the dynamic time warping to compare the 2 time series. And we found that on different days, the time signatures of a same path, they do not change very rapidly as compared to any other path in the same vicinity. Now the advantages to DDW is, once is we can compare time series of different lengths. So we can easily compare pre-stored road signature that may be generated or when captured at a different speed. And it can also, we can compare road signature when one is the subset of another. Now we consider all the possible scenarios, the way the user can reach a particular state by using different topography at different speeds. Maybe user may be coming to this point in the 8 different possibilities, maybe coming from R1 or maybe going away, maybe coming from this direction, another directions. Maybe user is moving very slow, have followed a different path, or maybe followed the 2 paths before reaching a state, or moving at a very high speed. It has covered the 2 paths in our database and rather than 1 path before encountering a stuck state. So in all scenarios, so when we compare, so this table represents one of the scenario that if we compare the user's movement, the barometer sensor's movements with the stored signatures, so the lowest values comes only when they are compared with the same road segment in the same vicinity. And from this, we conclude that we can easily get the path, we can estimate the path traveled by the user in this before encountering the stuck state. Now, taking it to further, we also did analysis to do the correlation analysis. We found that when phones are in the same vehicle, we got a very good correlation of the barometer readings. But if they are in a different vehicles and traveling one behind the other on the same road at the same speed, even then we got a good correlation value of 0.96. But if they're in a different vehicles traveling on the road, so maybe in the different speeds, then it ranges from this to this value. So high correlation comes only when they are in the same vehicle. And using this concept, we can tell when user has boarded a vehicle or not boarded a vehicle. So this information can be used and can be used in a, when user has boarded a bus, we can get to know, and when user has deboarded a bus or a taxi. So this information, by comparing the barometer values of the vehicle and the commuter. And same information can be used for the to find the occupancy rate. So to conclude that, we have proposed a strategy using the barometer sensor to detect the stuck state with a good accuracy. Further, we propose a majority voting to improve the accuracy further. And we have also proposed an approach to detect whether when the user has boarded a particular vehicle or not, and to find the occupancy of a vehicle. So thank you very much. So I'm open to questions.
Thank you so much for the presentation. I'm going to open the room for questions. Any questions in person here? No. I have a question for you. So you mentioned that you use crowdsourcing 3 slides ago, I believe, to decide some of your annotations. Do you know what kind of population do you need for that? Meaning, in your experiment setting, all of your vehicles were instrumented, or half of your vehicles are instrumented. Do you have any intuition behind what kind of instrumentation would you need?
Yeah, in our approach, the system that we have proposed, we are assuming that if many people are using our algorithm, so they will send the data to the server. Obviously, server would be busy in that case. We need to work on the scalability, that how quickly it has to be done, that how quickly, because if a lot of data is coming, so that scalability part need to be taken care at the server end.
Great, thank you. Just out of curiosity, go to slide number, your system architecture. You mentioned in your experiment setting, do you ask for people to annotate whether they're moving still at a manual basis? However, you do have the GPS information. Do you use that for annotation in this case?
Yes. When actually when the people are moving, so we have collected data on the 3 different cities in the California, in the Mumbai, and in the Chandigarh city of India. And then the people were moving around, and they actually annotated the data using the current GPS speed, and the current observation. There, we have also taken their current observation when they are labeling the data. So when they are, so actually even when the people are in the same vehicle, they can say that one may say that it is a congested and one may say that it is not congested. So we have taken care of all those labels, and when we have annotated all this data.
Great, thank you. There's one question here. Yeah, please go ahead.
Because you use the mobile phone, do you also see what is the power consumption, or because you do a lot of measurement with the barometer and the GPS?
Yes, the congestion detection algorithm actually it takes the barometer value. Barometer sensor, as a sensor, it consumes very less values. And if you have seen that the algorithm, it just based on only one jump feature which is calculated. Based on that, our model, which is very simple based on SVM. So so it gets triggered only when the when we get the stuck state, and only then the GPS is triggered for a few moments of time, and then the information is sent. And obviously when this obviously has to be on volunteer basis, the commuters who are moving around the cities, so if they volunteered enough, if they want to provide us this information, so based on that, so this on their smartphone, this can be used.
Yeah, but did you measure the power consumption?
No, we actually didn't measure the power consumption of our algorithm. For the algorithms, we have only considered that the barometer sensor as a whole, it consumes very less power, and we have not computed that how much power consumed when our algorithm runs on those phones.
All right, thank you so much, Naveen. Let's thank the presenter.
Thank you.
Moving on to the next one, we're going to listen to ApproxNet, Content and Contention Aware Video Object Classification System for Embedded Clients. It's going to be presented by Ran Shu, who is the final year PhD student at Purdue University. His research interest is the content, contention, and cost-aware approximate algorithms for mobile and embedded systems. He has first authored papers at top conferences like UCINIC, ATC, and SenSys. Today, he will present his latest paper accepted to appear at TOS. Go ahead, Ron.
Yeah. Can you hear me?
Yes.
Okay, good. So hello, everyone. In this presentation, I will introduce ApproxNet, a video object classification system for embedded clients, which is specifically designed to adapt to content characteristic, resource contention, and varying users' requirements. So my name is Ran Xu, and this is a joint work with Rakesh, Pengcheng, Peter, Ganga, Shumali, Subata, and Saurabh. So first, let me introduce the background of our vision system. We focus on the object classification system for streaming videos on embedded clients. This can be used in many cases. For example, a surveillance camera detecting airplanes in the scene, or a camera in the wild captures and detects antelopes in the national park. So the common requirement for such system are streaming and on-device, meaning that video frames are expected to be captured and processed at 30 frames per second in the real-time manner. And the object classification for every frame are needed, and the algorithm should not refer to the future frames as they are not available at the time of execution. And execution are expected to be on the device, which is typically an embedded board or mobile-like device with limited computation resource. So researchers and developers in the computer vision area have proposed many solutions for image or video object classification. So nowadays, convolutional neural network are the main solution, and top 5 errors rate have dramatically reduced over the year on the ImageNet dataset, which is one of the most widely used object classification and detection dataset. especially we look at the ResNet solution, which is a winner solution at the year of 2015 with the highest impact over the years. ResNet has several variants, either in 18 layers, 34 layers, 50 layers, or more. A general intuition is that the more layers lead to a higher accuracy. So recently, many more models have proposed with deeper and deeper neural network, achieving higher accuracy. However, we especially care the efficiency of the model on the embedded devices to achieve the real-time 30 frames per second speed. So some approximation must be done to improve the efficiency at the cost of reduced accuracy. One main motivation of ApproxNet is that when we look at the SOTA image or video classification models, for example, ResNet, we found that the video frame of different content complexity are best suited for different model configurations. So for example, for a simple video here, either using a computational heavy configuration or a light one do not make any differences. While for a complex video frame, we indeed need a deep model with large input resolution to correctly classify the frame. So the main challenge of ApproxNet is to dynamically adapt to the runtime conditions. So including the varying content characteristic shown here through the video stream, or the resource availability on the device, or different users' requirements. So an adaptive model system should lead the accuracy latency frontier in all conditions. To meet the need of switching between configurations, we categorize the solution into a one model and a multi-model design. So a one model design means a tunable model with some knobs controlling its operation points on the accuracy and latency. While a multi-model design typically use a collection of models and model variants and switch between them. For example, ResNet, VGG, and MobileNet, and each may come with several variants as well. So apparently, a multi-model design is straightforward, but considering the switching costs between configurations, we consider the one model design as one of the top priority, and it is a very challenging task to design, train, and optimize such deep neural network with tuning knob enabled. So given all these challenges, we propose an end-to-end system solution to address the problems. So given an input video frame in the streaming scenario, we design an approximation-enabled one-model DN and call it the executor. The executor comes with many execution branches which can independently run and classify the video frames. We then design a scheduler which decides which execution branch is the optimal one that satisfies the user's requirement. The scheduler comes with a frame complexity estimator and a resource contention estimator to handle runtime conditions. We will discuss these two in details later. To further reduce the cost of such online scheduler and estimators, we design an offline component, a profiler that collects the accuracy, latency, and switching overhead profiles and serves the online scheduler. So in this work, our contributions are in three folds. First, we design and implement, train, and optimize a one model approximation-enabled DN. So second, we design an end-to-end system that can adapt at runtime to varying content and content characteristics, resource contention, and users' requirement. So finally, our system is specially designed with low overhead and achieves accuracy latency frontier with the overhead considered and included. So let's dig into the design details. So first is our approximation-enabled DN. So the design principle is that it must be more efficient to be able to run with 30 frames per second on the embedded device, be accurate since we do not want to sacrifice accuracy too much, be adaptive so that we can use it for dynamic conditions, and with low switching costs to seamlessly switch between configurations. So we designed two tuning knobs. The first one is the input shape, which means how we resize the video frame and fed into the neural network. And the other is output, which means at which layer we want to get the classification results. And intuition is that smaller shape and early output can improve the efficiency at the cost of a reduced accuracy. So note that normally such DNNs do not allow a dynamic input shape or output at any intermediate layer. So we especially design our deep neural network with these features and train our approximation-enabled deep neural network so as such configurations can independently run always comparable accuracy. So we name the choice combination of a certain shape and output as an approximation branch, and we have 30 branches in our design. So given so many execution branches, we define the Pareto optimal branches as a branch standing on the accuracy latency frontier. Especially, we should be careful that such Pareto optimal branches are not static. The latency of each branch depends on the resource availability on the device and may vary differently under resource contention. The accuracy latency frontier also depends on the content characteristic, as the video frame of different complexity category may have different accuracy. So to make the system content aware, we design and implement a frame complexity category. So we use the age feature as indicator of the frame complexity, and each frame complexity category comes with its own Pareto frontier branches. For example, in the figure on the right side, we show frame in 4 different complexity categories. And each of the frame complexity category has its own Pareto frontier. So we also study how our system should adapt to the resource contention. So first, we need to emphasize that we treat the resource contention from other applications and the operating system as a black box and as a whole. So this choice has 2 advantages. So first, we do not need the system privilege to know the context of other applications, as the privacy, especially on the mobile and embedded device, is another important issue. And second, we ease the problem with 2 components, approximate and outside world. So our approximate only needs to adapt to the resource contention from the outside world, and thus can adapt to any known or unknown and any combinations of resource contentions. So to achieve this, during the offline phase, we use the benchmarking tools to generate the synthetic CPU and GPU contention to approximate and measure the latency of approximate under contention. So during online phase, we monitor the latency of approximate and estimate the level of online content contention level, and further adapt with optimal branches under such resource contention level. So finally, the scheduler as a core component to make the decision on which branch to run, solve the optimization problem of picking an optimal branch, which is subject to the accuracy A total with the content-aware accuracy A of branch B in content complexity category F, and contention-aware latency L of branch B in contention category C. The switching costs and system costs are also included so as the total latency is minimized in our solution. So especially we want to emphasize 3 key design elements in our system so that the system overhead is minimized. The first, our one model approximation enabled DN minimize the switching costs between branches since we do not need to reload any component of the model. The second, we reduce the overhead of the scheduler by an offline profiler. And finally, we reduce the overhead of the frame complexity category with a scene change detector, in which only when the scene in the frame change large enough, we recalibrate the frame complexity category. So otherwise, the category memorizer will take the past category as a proxy. So we evaluate our approximation enabled DNN on the LS-VRC image dataset with the image classification task, and our entire system on the LS-VRC video dataset with the video object classification task. We use the NVIDIA Jetson TS2 as our evaluation device. So for approximate and compared baselines, we mainly report 3 metrics: the top 5 accuracy on the test datasets, the per frame latency of the DN, including both the execution time of the DN and the system latency overhead. We compare approximate with a total of 5 baselines, reset of 2 variants, MCDN as a collection of light and heavy model variants, MSDNet as a multi-scale DN, MobileNet as an efficient DN, and NestDN as a multi-capacity DN. So we show the accuracy versus latency trade-off of the DN component on the image dataset on the left figure. We can see that approximate has the adaptive accuracy latency frontier between 15 and 40 millisecond latency on the embedded device, while ResNet and MSDNet cannot meet the real-time processing speed. The MobileNet, though being more accurate at some latency, is a collection of model variants and will suffer from the large switching overhead in the follow-up evaluation. In the right figure, on the video dataset, we study 3 typical usage scenarios, either a low latency, low accuracy, medium latency, medium accuracy, or a high latency, high accuracy scenarios. We can see that approximate is much faster than MCDN with the similar accuracy, and MSDNet again cannot meet the real-time processing speed, and so do the MCDN models. Further, we examine approximate in each frame complexity category. We observe that approximate provides a complexity category specific approximation branches which satisfy the 30 frame per second latency requirement and maximize the accuracy, while ResNet of either 18 or 34 layer cannot meet the 30 frame per second latency requirement. We evaluate approximate under resource contention by manually injecting the synthetic CPU or GPU contention and observe the temporal latency. We can see in the left figure that we test the 4 phases with varying CPU contention. Approximate shown in the blue curve has the latency below 33 milliseconds, while MCDN has much increased the latency under larger CPU contention. The same trend holds as we inject different levels of GPU contention in the right figure. Finally, we show that approximate is superior in terms of lower system overhead. In the left figure, we can observe that the latency spike at the time of switching in the MCDN baseline, but not in approximate. And in the right figure, we show that the overhead in approximate is negligible and takes a big portion in MCDN. We especially look at the switching overhead between execution branches in approximate and compare with NestDN, which also has a similar multi-capacity DN. We show that switching overhead of approximate is mostly below 10 milliseconds, rarely at 10 to 30 milliseconds, while NestDN comes with a 5 to 25 second switching overhead as we switch from a low capacity model to a high capacity one. So to conclude, as the era goes fast, there are better models and devices, new applications, and new users requirements. So we want to emphasize the key design methodology as a takeaway message, since they can apply to a new context and various domains. The first is our one model approximation enabled DN, which targets at higher efficiency on the device, higher accuracy, wide adaptability, and low switching overhead. This is the enabler of a system, and it is different from many vision models. Second is our end-to-end system design to adapt to runtime conditions. Particularly, we use a frame complexity categorizer to determine the content category and a contention sensor to determine the contention level. So depending on the application and device, these 2 modules can vary, and other feature models can also be considered. So on the other hand, the scheduler picks the Pareto frontier branches to minimize the latency at any desired accuracy level. So finally, our design to reduce system overhead is also a success factor that one should not ignore. Particularly, a one model DN reduces switching costs, the offline profiler reduces the cost of the online scheduler, and the online scene change detector reduces the cost of online estimators. So we hope our experience on the video object classification system can also help the design in many similar vision systems and broadly the approximate system. So thanks for listening, and I'd like to take any questions.
Thank you so much, Ron. I'm going to open the room for questions from the audience here. There's one question back there. Thank you.
Thanks for the talk. Can you clarify how you go from the frame complexity categorizer to predicting the accuracy of different models?
Okay. So I think I will use this motivation slides. Here, this is the frame complexity categorizer. So we first categorize each frame into several complexity categories. And for each complexity category, it has its own operator frontier. So basically, you can think about it, a simple frame can have one operator frontier that you can switch from, and a complex frame has another operator frontier that you can switch from. And the scheduler has this optimization function that given any desired accuracy level, you pick the one that minimizes the latency. So as a simple case, you can think about given any accuracy threshold in this curve, you will pick the one that minimizes the latency. So for each complexity category, you have a different operator frontier and can solve it with different optimal branches. And that is how we adapt to different content characteristics.
So, but ultimately, the accuracy depends both on the input complexity as well as your model capacity, right? So you would have to decide one frontier for every single model, like you have a number of baseline models that in your evaluation.
Yes, so there is a offline profile type here. We collect the offline latency profile, offline accuracy profile, and offline switching overhead profile. So the profiler will profile the model in a completely way so that we can know for each branch what is the accuracy of this branch, and given different content complexity category, what is the accuracy of them. So we know completely how those branches behave for different content characteristics. And then in the online phase, after we determine its complexity category, we can know its a better understanding of its accuracy.
Okay, thank you.
Thank you for the questions. There's another one.
That was a nice talk. Thank you. I have a question around the complexity of the system. You have 3 different models: resource contention estimator, frame complex estimator, and a scene change detector that you talked about. And then you have a scheduling optimizer on top. These seem to be pretty brittle. So if one of them is overfitting, is not doing the right thing, does the entire system break down? How do you make this entire system robust?
So I think I can use one example for the latency prediction branch in this figure to show how our system can be more robust. So you can see that in this main data flow, we estimate our contention levels through the resource contention estimator, and use this to determine a branch, approximation branch to execute. And then we also measure the runtime latency of those execution branch and feedback into the resource contention estimator. So it is actually a feedback loop so that our system can have a really better understanding of the runtime latency of those branches and adapt to it. So in this way, it is not like you offline profile it and just use it online. But we also receive the online signal so that our system can calibrate to the outside world or dynamic changes. Hopefully that can answer your question in one aspect.
Yeah, that does help. So that only applies to the resource contention estimator, right? Not the frame complexity, because you can't get the accuracy.
So frame complexity estimators have the assumption that the online content characteristics should also follow the same distribution of the online training dataset. So this part cannot may have the reduced performance if the online content characteristic is totally different from the offline training dataset.
Yeah, that makes sense. Thank you.
Thank you. There's one last question. We have time for that one.
If you have time. So thank you for your talk. So I was lost during the optimal branch. How do you define this optimality there? Or have you calculate? What is this branch at all? So let's say we have a VGG or ResNet.
So the optimal branches are defined among our 30 execution branches. So given a latency requirement, the maximum accurate, the most accurate branch is the optimal one, or given an accuracy requirement, the least latency branch is the optimal one.
What is the branch? So in ResNet, let's say we have 18 layers. Can you define what is the branch there? So up to 11, it's a branch?
Yeah, to define the branch, I will use this slide. So we have enabled two tuning knobs. One is the input shape, that how we resize the video frame to a particular shape and feed into the deep neural. And another knob is the output port, that at which intermediate layer we want to get the output. So a certain choice combination of the shape and output defines a particular execution branch. So think about it, you can either use 224 by 224 by 3 shape as the input, and use the output port 3 as the output position. And that is one execution branch.
So this is the sufficient depth so that we can get the highest accuracy as much as possible, right? The minimum depth that we need to get this accuracy.
So this only give you one execution branch. So just to study which branch is sufficient to give you accuracy target or a latency target, we will use this curve, the Pareto frontier curve, to pick the accuracy versus latency frontier, and then look at your accuracy target or latency target and check which branch will satisfy your requirement.
Okay, thank you. And my last question is regarding to the edge detection, something heuristic. Do you have any intuition why it works? So why you use this, probably the second derivative of the background, right? The scene detection edge.
Yes, so I think this is one of our trial to use edge features and for the content categorizer. So our intuition is that so for different complexity, edge feature will be very straightforward to characterize how complex is the video frame. And also, on the other hand, it is very come with low cost. So which is another consideration of our system. And we just test for different edge complexity category. And we truly see that the Pareto frontier are different, so that we can just use different Pareto frontier for each complexity category. And definitely different content feature extractors are also welcome in our system.
Okay, thank you.
Thank you so much for the questions. Let's thank the presenter.
We have one more.
Oh,
we have one more.
We got one more. We've got 1 minute.
Thank you for the presentation. I have a follow-up question, what's just been asked about the edge detection. So if you're basing your complexity categorizer on edge detection, have you tried on blurred images? Because there are many videos where people have blurred areas, and you cannot say that this is not complex enough because the edge detection was not given there. So have you tried that?
No, we didn't especially evaluate for blurred image. Each feature basically works in a large granularity, like a data set level. Given sufficient large amount of data, we can prove that with our edge feature is better than without. But for a particular video that say or image, say it is a blurred one, we cannot guarantee that our edge features will work for that particular case.
Okay, I have one more question, the last one. So you're putting one model on another model, and the complexity increases towards the end. Have you ever thought about how to make it interpretable for the users? Because at the end, you have to tell them that which feature is categorizing to the, or class contributing towards particular classification.
If you are talking about the approximation enabled DNA itself, it is not interpretable because that is another research area to make the deep neural network easier for humans to understand. But for our system, to understand its accuracy characteristic, latency characteristic, we truly have many tools to understand their spec. And especially in this architecture figure, we have a very complete profile, and we design the scheduler with the Pareto frontier. So in this way, we understand our approximation branches well. So this part is more interpretable.
So you say that from the input, you can trace the output at the end completely.
Yes, so for the input, we know it's frame complexity category, and we know the resource contention level on the device, and we know what is our estimation of for each branch, what will be the estimated accuracy and what is estimated latency, and then we choose a particular branch to run the executor and got the classification result. Right.
Okay, so, thank you.
Thank you so much. Now we can thank the presenter. Thank you, guys. This concludes the journal track 1 session. I think we're going to have a 30-minute break, and there's posters and demos outside, so enjoy. Thank you.
Thank you.
Thank you.
Thank you.
I think I should say. Sorry, I actually agreed to share the reference with this.
So are you that's almost 2 hours. So one is what yeah. That's what I did not see what was like that. I did not put like that.